Hello and welcome to Sleepy Science. Tonight we'll loosen the clock's grip and drift through 30 quiet astonishments. We'll watch moving things run a step ahead of where they are and feel the first second pause like a held breath. Let later moments repaint earlier ones and see cause and effect tucked closer together than seems polite. Notice the body prime in action before the eye arrives. Weigh altitude by how a tick changes across a stair and skim the sky to learn why fast flights borrow time. We'll meet matter that keeps a rhythm without doing work. Test how watching can freeze or hasten change, and let the order of first and then blur inside careful machines. We'll read a story from both ends at once and coax time from pure entanglement. Ask how quickly anything can truly become different, and face the brick wall that says there is no single dial for now. We'll teach atoms to answer in phase, measure height with clocks instead of rulers, and question whether a single object can behave more classically across its own past than math allows. We'll gather whispers that seemed lost and wait so long that a finite world nearly rhymes with itself. Then follow complexity as it climbs like a vine that marks direction when heat is quiet. We'll build when from statistics, hear the afterglow of sound, feel attention stretch and fold a minute, and watch one drawing flip between two truths as if time were the muscle that holds each turn. We'll separate the moment a choice is made from the instant we notice making it. Train the brain to arrive a beat early and tug at thought experiments that try to mail notes to yesterday. We'll wonder whether the cosmos ends with a bell or with silence, accept that at the same time only lives where signals can shake hands, and finally ask whether time is a bedrock or a fabric we weave. If this kind of gentle curiosity helps you rest, settle in, breathe once, and let's begin. Flash lag, motion that runs ahead. Blink and you'll miss it. The instant a stationary flash appears beside something in motion, your mind insists the moving thing is already a step ahead, as if reality skipped a frame to keep pace. This is the flash lag illusion, and it reveals that your perception of the present is built just far enough into the future to let you act on time. Start with the physical facts. Light from both the flash and the moving object takes tiny but real moments to reach the back of your eyes. Signals climb through the retina and along visual pathways. Neurons need additional milliseconds to agree on what they're seeing. And awareness itself is not a raw feed, but a brief synthesis. If the brain waited for perfect certainty at every stage, you'd be late for everything, from catching a ball to stepping off a curb. So your visual system estimates where a moving object will be by the time its evidence finishes processing. It doesn't guess wildly. It uses immediate clues like recent positions, speed and direction, and then it projects slightly forward, like a driver who looks a little down the road rather than at the hood. In classic demonstrations, a bar or dot moves smoothly while a brief flash appears aligned with it. Participants almost always report the moving item as ahead of the flash. Change the speed, and the size of the illusion tends to change too, because faster motion requires a longer extrapolation. Make the motion unpredictable, jitter, sudden reversals, or random speed changes, and the illusion shrinks because predictions become less trustworthy. Shift attention, and you shift outcomes. When people tightly focus on the flash, the lag can reduce. When they track the mover with attention or with smooth eye pursuit, the brain's motion signals become more confident and the perceived lead can grow or morph. Adjust contrast, brightness, or the timing of the flash relative to motion milestones, and you'll find the effect flexes. Evidence that multiple processes are cooperating. Rapid where pathways that favor motion changes. Slightly slower what-where loops that stabilize snapshots, and a final scene assembly that balances both. Several scientific accounts compete and partially overlap. One emphasizes motion extrapolation. To compensate for neural delays, the brain projects moving objects forward along their current path. Another highlights differential latency. Motion signals can reach position computing areas slightly faster than sudden flashes, so the moving thing is stamped into your awareness a heartbeat earlier. A third points to temporal integration and postdictive assembly. Your brain gathers a short window of evidence, then finalizes what you saw, allowing information that arrives just after the flash to nudge the final picture. You don't need to choose one story to learn from the illusion. Together they outline a sensible strategy for survival. Act in a world that's always a little ahead of your senses by leaning forward just enough to keep up. What makes this compelling is how testable it is without heavy math. If the effect were a simple mistake, it would behave randomly. Instead, it shows rules. When the moving object abruptly reverses direction right at the flash, the illusion can collapse or even flip, because the brain's forward model suddenly loses footing. When motion is smooth and continuous, the lag is robust. When motion is chopped into isolated jumps, the lag changes, mirroring the brain's growing doubt about continuity. Present two flashes with tiny timing differences, and you can tug perception toward one or the other outcome, showing that the brain is blending signals across a short, moving window rather than rubber stamping the very first inputs. Techniques that lightly disrupt the motion-sensitive stream, fatiguing certain detectors with pre-exposure to one direction, or crowding the moving object with distractors, also nudge the illusion's size, underscoring that what feels like "where is it right now?" is the result of a negotiation across specialized circuits. This is not a bug. It is a feature with a cost. In day-to-day life, the cost is tiny and the benefit is huge. You grasp a sliding cup before it falls, you time a catch, you avoid a collision. The flash lag illusion is simply the seam made visible when a prediction meets a perfectly timed interrupt. If you want to feel it for yourself, load a simple online demo of a rotating line with a periodic flash. Try tracking the tip with your eyes versus fixing your gaze on the center. Notice how pursuit changes the sense of alignment. Then ask what the illusion teaches, beyond a party trick. First, it teaches that now is not a single instant, but a constructed moment with thickness, a compromise between recent evidence and the near future your brain expects. Second, it shows that perception is not passive. It is an active model that runs slightly ahead, then corrects as more data lands. Third, it invites intellectual humility. Even when you feel absolutely certain that the moving object was already ahead, you're experiencing the brain's best bet, not a time-stamped photograph. And yet there's a gentle reassurance here, a reminder that useful accuracy often beats frozen certainty. The world doesn't wait for you to become sure. It moves. Your mind moves with it by forecasting just enough to keep your hands, eyes, and steps in sync with a future that is arriving. Picture it like walking at dusk. You can't see every pebble, so you read the texture of the path and plant your foot where the next patch will likely be. Once you're there, you adjust. That's not deception, it's skill. The flash lag illusion pulls back the curtain on that skill, letting you notice the quiet calculation that normally protects you from delay. And if part of you wonders whether living slightly ahead is risky, consider the alternative of living slightly behind. Late to break, late to catch, late to learn. Better to meet the next moment halfway and revise on contact. So breathe, soften your focus, and let the insight land. Your experience is not late, it is timely by design. A small act of trust your brain extends to the moving world. The flash makes a demand for perfect alignment. Your perception offers something wiser, actionable alignment. In that trade, you gain a life that stays in rhythm with change, and you lose only the illusion that seeing is ever purely instantaneous. Chronostasis, the stopped first second. Look quickly at a ticking wall clock and you may feel a tiny miracle. The second hand seems to freeze right after your eyes land, as if the world waited for you to arrive. This fleeting stall is chronostasis, and it exposes a quiet edit. Your brain performs whenever your gaze jumps from one place to another. In the span of a blinkless dark called a saccade, your eyes pivot hundreds of degrees per second, yet you never see the scene smear across your vision. Instead, for roughly a few dozen milliseconds before and after the jump, your visual system downweights or suppresses what would otherwise be a blurry trace, and then knits a stable moment from the first clean image that follows. That first clean image is important. It doesn't just mark the beginning of your new look. Your awareness stretches it backward to cover the gap you didn't witness, which makes that first second feel longer than it truly was. Researchers show this by asking people to glance from a fixation point to a clock or a counter with a smoothly stepping indicator. The very first tick often seems to linger, while subsequent ticks feel regular, evidence that the mind has extended the fresh frame to fill the silent passage through which the eyes were in flight. Behind the scenes, a packet of signals prepares the jump. Motor plans in frontal eye fields and superior colliculus. A copy of that plan, called efference copy or corollary discharge, broadcast to visual areas, and a temporary gating in relay stations like the thalamus, all coordinating to prevent motion blur from corrupting your sense of a steady world. Because your brain aims for continuity, not raw footage, it chooses to protect the larger story, the stable scene you believe you're inhabiting, even if that means retroactively lengthening the first instant after you land. Chronostasis isn't a visual-only quirk. Similar stretches show up in Audition and Touch when attention and rapid shifts are involved, hinting that the brain's timing is not a single clock, but a collection of specialized stopwatches that reconcile actions with sensations. Crucially, this is not deceit for drama. It's an elegant compromise with physics and biology. Photons don't wait, but neurons need processing time. Rapid movements would otherwise smear the retina with meaningless streaks, and your behavior benefits from a world that appears steady, even while your senses are repositioning. The cost of that steadiness is a subtle recalibration of subjective duration right at the point of arrival. This duration expansion is most noticeable when the scene offers a precise rhythm, a ticking second hand, a flashing LED, a metronome on a screen, because the longer feel of the first interval contrasts against the following regular ones. Alter the conditions, and you alter the illusion. Shorten the saccade by moving your eyes a small distance, and the extra feeling often shrinks. Increase cognitive load, and the effect may waver because attention is already occupied. Use a display with low contrast or unstable edges, and the anchor you land on is weaker, giving the brain less to stretch. There are also fascinating limits. If the indicator you land on jumps unpredictably right as you arrive, your brain has less confidence to backdate a clean moment, and your sense of the first interval becomes less inflated. Showing that certainty about the new frame, the trust that it is a good anchor, matters for the warp in perceived time. You can test this at home with a phone stopwatch and a simple routine. Fix your eyes on a dot, then flick to the running seconds. Compare the feel of the first second with the next 3. Repeat with different saccade distances. Or try landing on a digital clock that changes more abruptly than a sweeping hand. You'll likely notice that crisp, step-like changes give your mind a more decisive first frame, boosting the expansion. Why should you care beyond curiosity? Because chronostasis reveals a principle that quietly shapes daily judgments. The brain optimizes for continuity and usefulness, then reconciles time after the fact. Consider user interfaces that expect immediate responses after you look. If the first beat feels longer, designers can inadvertently make on-landing animations seem sluggish or snappy, depending on how they align with your arrival. In sports, an athlete's eyes hop between ball, opponent, and target. The first moment on a new object could feel slightly more spacious than it is, affecting how swiftly a movement is launched, unless training accounts for the bias. In conversation, your eyes spring between faces and gestures. The first heartbeat of a new glance may feel more pregnant with meaning, adding weight to fresh expressions. None of this means your sense of time is broken. It means your sense of time is negotiated, balancing precision with the need for a seamless scene in which action makes sense. To understand the negotiation, imagine editing a film live while filming it. When the camera pans rapidly, you cut away from the blur and hold on the next clear shot just a little longer to maintain rhythm. The story flows. The audience never sees the smear, and the cut feels intentional. Your brain is doing this editorial work for you, guided by signals that predict your own eye movements and briefly gate distracting inputs. Then holds the first stable frame you land on, so the narrative of the world stays coherent. Notice the philosophical echo. The present you experience is not a raw slice of physics. It is a present with craftsmanship, one that smooths the gaps your actions create. The proof is as ordinary as glancing at a clock, yet as deep as any question about consciousness, because it shows your awareness is not merely late or early, it is actively composed. And that brings us to a gentle close. The next time the second hand seems to halt to greet you, take it as a friendly courtesy from a brain that cares more about a continuous life than a perfect timestamp. You are not being fooled for spectacle. You are being escorted across a tiny canyon, your own movement carved. On the far side, the world feels whole again, and you can move through it with confidence, having learned that even the first second, especially the first second, can be longer on the inside than on the clock. Backward masking. Future frames edit past. You think perception stacks up like pages in a book. First page, then the next. But there is a stranger editorial rule at work. If a brief image is shown and, a whisker of time later, a strong pattern splashes over the same place, the latecomer can block the earlier one from ever reaching awareness, as if the future frame reached back and rewrote the past. This is backward masking, and it's one of the cleanest demonstrations that what you consciously see is decided after a short audition, not the instant photons arrive. In a typical lab scene, a simple target, say a letter, a shape, or a faint picture, appears for just a few milliseconds. Before your conscious mind can stabilize it, a mask arrives, a grid, a jumble of fragments, a ring of dots, or a bright pattern that overlaps the space. When the gap between them, the so-called stimulus onset asynchrony, is short enough, tens of milliseconds, the report of the first item plummets, even though the eyes and early visual pathways did register it. This is not a trick of poor eyesight. It is a selective interruption in the chain that turns faint, local activity into a stable, shareable experience. The early part of the chain is fast and mostly feed-forward. Signals climb from the retina through relay stations into areas that map edges, orientations, and simple features. If left alone, those signals would bounce in loops with higher regions, refining and amplifying the pattern until it ignites a wide network that you experience as seeing. The mask barges in right before that ignition completes, overwhelming or decorrelating the pattern so the loops never lock on, and the target never gets a seat at the table of awareness. You can feel how real this is by how systematic it behaves. Make the target brighter or last a little longer and it survives. Slide the mask later in time and the target escapes. Move the mask so it barely fits around the target without touching it and it still works, meaning the mask doesn't need to paint over the target to defeat it. It only needs to disturb the circuits that would have confirmed it. Because the decision about consciousness is made after a short window of evaluation, late information can veto the earlier candidate. Vetoed does not mean erased from the brain. Masked targets can still prime behavior. People can be faster at naming a masked word's meaning, or quicker to respond to an arrow pointing left if a masked arrow pointed left a moment before, even though they swear they saw nothing. This shows a critical split. Some processing gets far enough to shape decisions and motor readiness, but not far enough to become a vivid, reportable sight. Vary attention, and you vary the effect. When observers are busy with another task, or when the mask steals their focus, suppression is stronger. When attention is guided to the target's location and time, the window can widen and the target sneaks through. Tune contrast and complexity, and you can flip the outcome. A simple ring might mask poorly. A tightly tailored pattern that shares contours with the target might mask brutally. Present the mask before the target, and you learn a different lesson about fatigue and lingering noise. Presented after, and you learn about how consolidation can be cut off. The timing map matters. In many studies, masks delivered about 50 to 100 milliseconds after target onset create the strongest disruption, while stretches longer than that let the target stabilize. This is a clue to the duration of the brain's decision window. Electrical and magnetic recordings back that timeline up. Brief responses to the target appear early, but the later, widespread burst that usually marks conscious access is shrunk or missing when the mask wins. None of this requires exotic math to appreciate. It is enough to grasp that awareness is a gate that opens only when a candidate pattern survives long enough, in the right company, with the right reinforcement. Backward masking is useful beyond laboratories. It explains why cluttered signage fails at a glance, why subtitles on busy backgrounds become tiring, why a traffic warning that briefly appears before a bright reflection can be missed even by alert drivers. Designers exploit the insight by giving important items a protected moment. A clear background, a short delay before other elements animate, a gentle transition that doesn't drown the message. Coaches and educators can build drills that isolate a target before adding surrounding movement, letting the brain learn a shape's identity before distractions arrive. Then they can close the timing gap to train resilience. Even art and cinema leverage the principle. A quick insert followed by a visually loud cut might be sensed without being fully seen, steering mood and expectation right under the surface. Backward masking also invites philosophical courage without hype, because it forces you to accept that your experience of what just happened is issued after a brief editorial pause. That pause is not deception, it is quality control. Your brain prefers to publish a coherent scene rather than a flicker of half-confirmed hints, so it waits just long enough to collect late evidence, then signs off. Most of the time this gives you a cleaner, more useful world. Sometimes it costs you a glimpse that truly occurred. If that feels unsettling, consider the alternative. A consciousness that reports every fragment the instant it arrives would be noisy, contradictory, and dangerous to act on. The mask's ability to cancel a target while preserving its quiet influence shows how layered your mind is. Fast pathways already nudging behavior, slower loops deciding what's worth showing to you. And there is a gentle reassurance hidden in the mechanics. Because the rules are law-like, you can work with them. You can adjust timing, contrast, and context to make the crucial thing win the audition. You can give your own thoughts a similar grace, allowing a breath of time before you decide what you saw in a tense exchange or a messy feed of information. Truth does not vanish because a mask arrived. It simply needs the conditions that let it stabilize. So when you hear that the future frame edits the past, don't imagine magic. Imagine a sensible, timed competition in which later evidence can still change the verdict about an earlier candidate. Your experience is the published version of that trial, released on a short delay so it reads as a story rather than static. Knowing that, you come away not with cynicism, but with a practical respect for the way minds protect clarity. By letting the mask win when it must, and by arranging the scene so the signal you care about is given the precious few milliseconds it needs to become real. Temporal binding, cause effect squeezed. Strike a key, hear a tone a breath later, and notice something subtle but profound. When you believe your action produced that sound, the gap between them feels smaller, as if the mind tugged cause and effect toward each other to fit them inside one moment. This is temporal binding, the quiet compression of time that appears when you experience agency, and it teaches you that the timeline you live by bends to preserve stories of making things happen. The basic demonstration is disarmingly simple. People tap a button, and a tone follows a couple of tenths of a second later. When asked to report the exact instant the tap occurred, they place it slightly later than it really was. And when asked for the instant the tone occurred, they place it slightly earlier than it really was. Link the two as cause and effect, and they slide closer together in awareness, like bookends that lean inward. Unlink them, play tones randomly regardless of taps, and the squeeze relaxes. The perceived times move back toward their true positions. That shift is small in clock units but large in meaning. Your brain appears to keep a compact ledger for events it interprets as yours, settling the action and its outcome into a shared frame that reads as one deed. This isn't a trick of memory after the fact. It shows up when judgments are made immediately and when attention is carefully controlled. It survives changes in the exact delay, and it can be measured with rotating clocks or timed reports that pick out a single moment with fine granularity. The pattern deepens when you adjust the sense of agency. Increase the feeling that the outcome depends on you. Make the tone more predictable after your tap. Give you control over which tone will follow, or embed a small choice, and the binding grows stronger. Water down the causal link. Make the tone occur only sometimes, or let it appear with the same probability whether you act or not. And binding weakens, sometimes to the point of vanishing. Even the character of the outcome matters. When the consequence feels negative or punishing, some people show reduced binding, as if the mind distances the event rather than adopting it. When the outcome is helpful or confirms a goal, binding can increase, as if ownership tightens the bond. These regularities hint at a pragmatic rule. The mind protects a sense of authorship by tidying the timeline whenever it can plausibly claim that that the same hand set both ends of the sequence in motion. Under the hood, there is an elegant idea that keeps the explanation grounded without drowning you in math. The brain is constantly asking a simple question: do these two things belong to the same cause? And when the answer is likely yes, it favors a single, clean account. A brief delay between your move and the world's reply is no contradiction if the system expects delays in tools and bodies. Still, any gap invites uncertainty, and perception often answers uncertainty by leaning events together, rather than leaving a crack that would weaken the feeling of control. You can think of it as an internal editor applying a same cause template. If the button press and the tone fit the template, right order, plausible delay, anticipated content, the editor centers them on a shared beat so the story reads smoothly. That smoothing is not free. It changes the apparent timing in ways we can test, and the changes carry signatures of how you felt about your role. In clinical research, these signatures have become a window into agency. People who struggle with an exaggerated sense of influence sometimes show stronger binding, even when outcomes are not under their control. Those who feel less in charge show weaker binding, even when they could have claimed the effect. In certain movement disorders, binding can be altered by how well the nervous system predicts its own motions. In some forms of psychosis, binding defies the usual rules about probability and delay. These findings are not diagnostic on their own, but they demonstrate that the squeeze of time can serve as a behavioral clue to the self's confidence in its causal reach. The phenomenon also scales with the medium of action. Replace physical taps with brain-computer interfaces or virtual hands, and binding still appears if the system responds reliably. Degrade the reliability or inject jitter, and the sense of authorship and the amount of compression both fade. That pairing matters for the technology you use every day. Game designers and toolmakers know that consistent, low-latency feedback preserves the feeling that I did that, while inconsistent or contextless feedback erodes it, making outcomes feel late and separate. Subtle design choices, tiny audio cues aligned with expected latency, haptic nicks that land just as a change appears on screen, confirmations that mirror the predicted type of outcome, can keep the mind's editor in agreement with the machine. So your actions and their consequences share a beat even when the network or device cannot be instantaneous. In classrooms and labs, temporal binding also becomes a teaching instrument for causality itself. When students manipulate systems, electrical circuits, simple simulations, musical loops, clear and consistent contingencies shrink their subjective gaps and strengthen learning. Muddy contingencies stretch the feeling of separation and slow the grasp of what does what. In eyewitness contexts, the lesson cuts the other way. Because belief about who caused what can tighten or loosen perceived timing, interviewers must avoid suggestions that imply agency before witnesses estimate when things happened, or else their timelines may shift to match a story they feel compelled to endorse. There is a thoughtful twist here that will serve you long after the examples fade. Temporal binding shows that your experience is more than a timestamp. It is a claim, this is mine. And the claim reaches backward and forward across a small span to make sense of worldly change. That claim can be wise or mistaken. Wise, when your action truly carries the outcome and the compression simply reflects how the mind lives alongside small, expected delays. Mistaken, when your action is not the cause but the brain pulls events together anyway, seduced by pattern or by desire. You can feel the difference with a home experiment. Set up 2 conditions on a laptop or phone. One in which your click always triggers a sound after a fixed short delay, and another in which sounds arrive with the same rhythm whether you click or not. After a few trials, you are likely to report a tighter felt gap in the first case and a looser one in the second, even if the raw delays are identical. Then notice how quickly the effect follows confidence. As soon as you doubt that the sound depends on you, the squeeze relaxes. Now reflect on the wider life. When you practice an instrument and the strings answer your fingers reliably, your sense of driving the sound pushes cause and effect together, making the music feel under the hand. When latency creeps into a video call, the same brain that once closed the gap opens it, and you feel oddly detached from your own words. When you mentor someone and see them succeed, a strong feeling of influence can compress the lag between your guidance and their achievement in your memory, strengthening ownership. When outcomes are less clearly tied to your input, the timeline stretches and you release credit. None of this is mystical. It is the nervous system maintaining a workable map that honors both action and evidence. And at the tender edge where philosophy meets daily living, temporal binding offers a gentle challenge. Perhaps free will is not merely about choosing in isolation, but about aligning the world so that your choices and their effects can be read as one movement. That alignment is partly out there in devices, teams, and habits that respond, and partly in here in the way you interpret contingencies. The practical takeaway is kind and concrete. If you want to strengthen the feeling of authorship in your craft, tighten the contingencies. Practice with feedback that is clear and timely. Arrange tools so their replies are consistent, and name the outcomes you intend before you act, so your mind can compare what happens to what was expected. If you want to loosen undue ownership in situations where outcomes are shared or uncertain, widen the window. Admit alternate causes, label probabilities, and resist rushing to glue events together just because you were nearby. In both directions, you are not changing time. You are shaping the narrative hook that decides whether cause and effect sit on the same beat. And that brings us to a calm close. Temporal binding does not claim that the future edits the past. It shows that belief about making something happen edits the experience of the gap between them. The world keeps its order, action, delay, consequence. But your awareness tucks them close when the story of "I did that" is strong. Recognizing the squeeze does not cheapen responsibility. It clarifies it. You learn to design your environment for honest control, to watch for false tightening when you want to feel powerful, and to accept true distance when outcomes are not yours to claim. In the space of a few heartbeats and a simple tone, you glimpse how a sense of self keeps time, and how wisely tending that sense can make you both more effective and more humble. Readiness, potentials, before choice. Before you decide to wiggle a finger, a faint electrical tide in your brain has often already begun to rise, and that quiet swell, called the readiness potential, has become one of the most unsettling clues about how choices actually come to life. First seen in the 1960s by researchers measuring scalp signals over motor areas, the readiness potential is a slow build-up that precedes voluntary movement by a few hundred milliseconds, sometimes more. Decades later, experiments that asked people to make spontaneous flicks and to report the instant they felt the urge added a twist. The brain's build-up tended to start well before the reported moment of intention. It is a simple setup with heavy implications. Sit relaxed, choose any time you like to tap, watch a rapidly moving clock, and later tell the experimenter when the urge to act appeared. On average, the neural ramp is already climbing long before your subjective now of deciding. That headline has been repeated so often it can sound like a verdict on free will, but the closer you look, the more nuanced and instructive the story becomes. First, the signal itself is small, noisy, and typically revealed by averaging many trials. You don't get a crisp decision spark. You get a slow drift that becomes visible when many little waves line up. That invites a better question than who's in charge, namely, what does the brain need to do before a movement, and how does that preparation feel from the inside? One influential idea says the readiness potential is not a pre-written command, but the signature of an internal accumulator. Background fluctuations in motor-related circuits wander until they cross a threshold, at which point a movement is triggered. When you ask people to act whenever, their brains are effectively waiting for the wandering activity to climb high enough, and the average of many such climbs looks like a ramp. This view makes grounded predictions that match the data. When people are told to act sooner rather than later, the baseline nudges upward and the climb shortens. When they are told to space actions out, the baseline dips and the weight grows. Manipulate attention, fatigue, or uncertainty, and the patterns shift in ways an accumulator would. It also explains why movement-related signals recorded closer to the muscles, the tiny pulses in the spinal cord, or the first hints of electrical activity in the finger, arrive last. There is a cascade from broad preparation to focused commitment to muscle execution, and the scalp only sees the earlier, blurrier part. Still, there is more to the tale than a random walk. If the readiness potential were merely idle noise, it would not carry any information about which hand a person will move. Yet subtle patterns known as lateralized activity tilt toward the side that will act. And with sensitive methods, researchers can predict the chosen hand above chance before people say they have decided. Other groups using brain imaging have reported that signals in frontal and parietal regions hold weak but real hints of an upcoming choice seconds in advance in tasks where the options are deliberately meaningless. Crucially, those predictions are far from perfect. They hover just over coin flip accuracy. And they don't fix the exact moment of action. They reveal a bias developing in a competitive system, not an iron law being executed. That matters for what you should carry away. The brain does not appear to post a finished command and then inform you late. It appears to cultivate conditions in which certain actions become more likely until one wins, and the feeling of willing that action seems to arrive as those conditions pass a point of no return. The timing of the urge is also hard to pin down with the precision we might wish. Reporting a moment of intention requires introspection plus a moving clock. Tiny delays in perception or attention can shift that report by tens of milliseconds. Change the way you ask. Use different clocks, phrasing, or training, and the reported time often moves, even though the movement and the neural signals are the same. That doesn't invalidate the finding. It reminds you that subjective timing has its own noise and rules. Meanwhile, a different line of evidence keeps the conversation honest. If you deliver a brief pulse of magnetic stimulation to motor cortex at just the right instant, you can delay or even cancel a movement that was otherwise about to occur, indicating that there is a narrow window in which an action is prepared but still vetoable. Even the original experimenter emphasized this veto. Conscious control might not initiate the earliest build-up, but it could still stop or redirect an action before it completes. You can feel the practical truth of that idea outside the lab. A hand reaching for a phone during a meeting can be halted by a thought. A foot starting to press a pedal can be pulled back by a flash of red. Preparation is not destiny, it is readiness awaiting permission. The readiness potential also teaches humility about how we construct reasons for simple actions. When a task is stripped of meaning, move whenever you feel like it, people often confabulate a reason after the fact because we are storytellers by nature. Add even a small reason, a goal, or a consequence, and the landscape changes. In more ecological settings, choosing words, planning a path, deciding whether to speak, multiple networks weigh value, memory, and social context over longer timescales, blending slow biases with fast thresholds. That is why no one has convincingly shown a reliable, second-by-second neural fate map for rich, real-world choices. The brain's preparation is distributed, context-sensitive, and probabilistic. The important lesson is not that you are an audience to a puppet show, but that your experience of deciding is the conscious surface of a layered process that began earlier, involved many contributors, and culminated in a movement only when conditions aligned. From this angle, the readiness potential isn't an enemy of freedom. It is a window into the cost of acting. The nervous system must collect and shape activity so that an action can be launched on demand. If you want that launch to be timely and safe, your brain must live near a poised state. Ready to go, yet interruptible. That poised state shows up as the slow wave we've been discussing. With this framing, the practical implications become clear and surprisingly hopeful. Training that clarifies goals and consequences can shift baselines so that useful actions are easier to initiate and harmful ones are easier to veto. Designs that minimize uncertainty and latency reduce the need for high risky readiness. Habits like pausing before sending a message create a deliberate veto window that protects long-term aims from short-lived impulses. Even ethics can borrow from the physiology. Responsibility thrives not in denying preparation, but in managing it. By choosing environments, rules, and routines that shape what builds up before the moment of choice. So the next time you notice a decision forming, your hand hovering over a link, your mouth about to interrupt, remember what the readiness potential quietly reveals. Beneath the calm surface of "I choose" lies a patient, dynamic preparation that can be steered. You are not late to your own life. You are arriving at the crest of a wave you helped generate through attention, expectation, memory, and values. See that wave early, and you gain room to refine it. Ignore it, and you may mistake momentum for fate. In that small, teachable interval before action, freedom takes its most practical form, not as a magical spark outside the brain, but as skillful guidance within it, turning readiness into a choice you can own. Jet-lagged atoms, redshift at meters. Stand on the ground floor while your friend takes the stairs, and something almost impolite happens. Their seconds run a touch faster than yours, not because they're fitter, but because they're higher, and even a few meters of altitude nudge time itself. Physicists call this gravitational redshift, and the most sensitive clocks we've built can feel it over the height of a human. At heart, the idea is simple. Gravity isn't just a downpull, it's a warp in the stage on which all rhythms play. Deeper in that warp, every process slows a hair. A clock counts by repeating something steady. An atom's light, for instance, which flips between two energy states at an absurdly regular rate. When that atom sits lower in a gravitational field, its rhythm drags compared with the same atom perched higher, and its light slides to slightly longer wavelengths, a tiny red shift that tells you the clock's heartbeat has slackened. This isn't poetry. It's a laboratory fact that began in classic tests where photons had to climb a tower and arrive just a little less energetic than when they started. Later, physicists learned to stop sending light up and down stairwells and instead compared co-located optical clocks, each one a cathedral of lasers and vacuum chambers tuned to a single atomic transition. With care, two such clocks stacked just a meter apart disagree by a measurable amount, and modern versions can register the difference across the span from your heart to your head. The metaphor of jet-lagged atoms fits because the effect feels like travel fatigue written into the universe. Lift an atom by a short distance, and it wakes up into slightly faster time. Drop it back down and it dozes into slower time again. Techniques to do this are elegant and strangely beautiful. Cold atoms are levitated in standing waves of light, held in lattices like birds on the rungs of an invisible ladder. By probing how the frequency of their light shifts as you adjust the rung, you watch gravity reach into the atom's metronome and retune it by parts in a quadrillion. In another line of work, neutral atoms are spread over a few millimeters in a single trap and read out with microscopic resolution, revealing a gradient of time within a thumb's width. None of this requires equations to appreciate. Think of time as a river that quickens slightly with altitude. Even the few meters between floors make a difference that a good clock can taste, and the whole planet stars in the experiment. Live on a high floor, and, over a lifetime, you gain a tiny fraction of a second on your downstairs neighbor. Fly across an ocean, and your watch will disagree even more thanks to altitude and motion together. Satellites must constantly correct for both effects, or the navigation on your phone would drift wildly. What makes the story compelling is how testable it is. Change the height and the shift changes with it. Move the clock, and special relativistic slowing from motion joins the dance in exactly the amounts expected. Improve the clock's stability and the once invisible becomes ordinary data. This is where the frontier gets exciting, because time bends with gravity, and gravity tracks mass. A web of ultra-precise clocks could one day map underground water, rising magma, or even tectonic strain by watching how local time subtly speeds up or slows down as the Earth redistributes its weight. In that vision, geophysics becomes timekeeping, and a city's safety might be guarded by listening to the tick of atoms across rooftops. There's also a quiet philosophical lesson here that costs nothing to carry. We usually treat time as a single drumbeat that everyone hears the same, but the world is kinder and stranger than that. Your seconds are not identical to mine if we stand at different heights. Your life is braided with gentle variations that never announce themselves, but shape the rhythm of everything from light crossing a room to signals orbiting a planet. Even in your own body there is a soft tilt. Your head ages imperceptibly faster than your feet, an effect too small to feel, but well within the grasp of today's instruments. That realization doesn't make time meaningless, it makes it richer. It says that now depends on where you are and how you move, that maps need clocks as much as clocks need maps, and that the universe keeps its promises with exquisite specificity rather than bland uniformity. If there is something to take into your day, let it be this. Precision doesn't drain wonder, it deepens it. A meter's worth of altitude can rewrite a clock. A handful of atoms can arbitrate the truth. A device on a lab bench can weigh the pull of the Earth without ever touching it, simply by listening to the color of a whispering ion. You do not need to master the machinery to let the idea reshape your intuition. Look up a staircase. Picture time as a tide that rises ever so slightly with each step, and feel the room grow larger. The future is not far away. It's a floor above you, arriving a fraction sooner, waiting with a smile for your slower second to catch up. Time dilation in fast flights. Lean back in an airplane seat and realize you've signed up for a tiny physics experiment. While the cabin hums and the map crawls across the screen, your onboard seconds are quietly slipping out of sync with the seconds of the people waiting for you on the ground, because at high speed time itself slows a breath. This is kinematic time dilation, the speed-driven kind predicted by relativity, and although the effect is small at airline velocities, it is real, measurable, and woven into technologies you use every day. Begin with an intuition you can trust. Motion is not just a change of place, it is a way of tracing a path through space-time, and different paths give different totals of experience duration. Sit still in an airport lounge, and your personal clock racks up a certain count. Race through the sky in a pressurized tube, and, compared with the lounge, you accumulate slightly fewer ticks between departure and arrival. You do not feel this, because your biology and your watch are both on board, slowing together. Only a careful comparison with a clock that took a different path, say one left on the ground, can reveal it. Physicists learn to make that comparison with exquisitely stable atomic clocks, and the verdict is consistent. Speed shaves time. Early demonstrations piggybacked on commercial flights, ferrying portable clocks eastward and westward around the world, and then matching them with clocks that stayed home. Later experiments cranked the precision up with dedicated aircraft, faster jets, and ever more stable oscillators. Across these tests, a pattern emerges that is both subtle and elegant. When you fly fast in the direction Earth is already rotating, your absolute speed through space increases, and you come home having lost a whisper of time relative to the ground. When you fly the opposite way, you peel some of that speed off and can return having gained a whisper, a sign that less motion yields more experience duration. Add altitude to the picture and the story grows richer without growing confusing. High up, gravity's pull is a touch weaker, which by itself makes time run slightly faster. This altitude effect pushes flight time the other way, opposing the slowing from speed. On a typical airliner, both influences are present at once, and whether you gain or lose net time depends on the route and direction. Cruise fast enough, and the speed penalty wins. Climb high and linger, and the altitude bonus creeps back. Precision is not the point for you as a traveler. No one misses a meeting because their wrist aged by a few dozen nanoseconds. But precision is everything for the engineers who must line up clocks that sit in different states of motion all the time. The best illustration is orbiting hardware. Navigation satellites zip along rapidly and sit far above the ground. Their onboard seconds would drift away from earthbound time by kilometers in daily position error if left uncorrected. Designers pre-adjust the satellite's clock rates and then keep trimming with updates so that when your phone listens to their signals, it can triangulate you to a driveway. This is not a one-off proof. It is a continuous, global admission that time dilation is not a philosophy debate, but a calibration. You cannot skip. You see echoes of the same physics in high-speed trains equipped with research clocks, in timing networks that link laboratories on fiber optic lines, and in particle accelerators where unstable particles live longer when hurled near light speed, surviving long enough to be studied only because their internal watches slow in flight. None of this requires you to juggle symbols or memorize formulas to appreciate what's at stake. Think of time as something counted by processes, atoms flipping states, quartz crystals trembling, hearts beating. If two travelers depart together and reunite after following different motion histories, those processes will tally slightly different totals, not because one was damaged or lied, but because how much time passed is not absolute. In the quiet language of physics, each traveler carries a personal measure that depends on their motion. In the vivid language of daily life, it means your experience of duration is honest inside your path. and only shows its difference when compared across paths. That comparison is what aircraft give us, a way to rack up enough speed for long enough that the gap peaks above the noise floor of good instruments. Engineers turn the gap into a tool. Intercontinental timing companies synchronize financial trades by moving signals along undersea cables and along air routes, correcting for the fact that moving clocks and moving messages do not keep perfectly aligned rhythm. Radio astronomers spread telescopes across continents and stitch their recordings into one giant dish, demanding clock agreements so strict that even the faint slowing from motion enters the budget. Power grids coordinate phase across regions, using timing references that must remain coherent, despite the ever-moving platforms that generate and relay them. Even in medicine and neuroscience research, where precise timing of stimulation and sensing matters, control systems inherit the discipline forged in navigation and communications. Motion of platforms, whether an aircraft or a table-mounted arm, is accounted for because timing tolerance is the difference between a crisp result and a blurred one. What makes the airplane case compelling as a story for your intuition is how benign and everyday it is. You board, you read, you doze. Nothing in your body announces your time is slowing. And yet, under the carpet, a ledger is kept. The reason you cannot feel the difference is not that it is imaginary. It is that your entire local world, your neurons, your pulse, your watch, belongs to the same packet of motion. To notice the effect, you must design a reunion, a comparison with another clock that walked a different path. That need for reunion is the deeper lesson to carry. Truths about time are relational. They show themselves at the join between stories. This is why popular puzzles like the twins thought experiment are instructive rather than paradoxical. Rank all the segments of the journeys by their motion and their acceleration. Write the bill for each, and when the twins meet again, the totals differ by exactly the amount the theory predicts and the experiments verify. The moment you accept that, you unlock a practical mindset. If a system in your care depends on timing, an instrument, an algorithm, a network, you ask where the clocks move and how fast. You expect to correct for motion whenever you stitch together data from platforms that do not share an identical path. You treat time not as a single drumbeat but as a choreography that needs a conductor. For a traveler, the payoff is softer but real. Respect for the quiet complexity that holds your trip together. Navigation works because a ring of machines in the sky keep their seconds honest relative to Earth while skating around it. Flight control works because radar and radio messages are timestamped against common standards. Even the constellation map on your seatback is a promise that your path through the air has a clock-aware shadow in the ground's computers. And there is a human reflection worth keeping close as you descend toward the runway. Speed shortens your personal tally of duration, but the point is not to hoard time by moving slowly, nor to gain life by avoiding jets. The point is to see that your sense of a single, universal now is a useful habit, not a law. We share time by careful agreement, by aligning clocks that move differently, by declaring standards that bridge paths, by building systems that notice when a platform's seconds drift from the networks. Your flight home is one path among many. Your life is a weave of such paths. Knowing that they do not all keep the same count is not alienating. It is empowering. It lets you understand why your phone can find a cafe on a map, why an observatory on one mountain can whisper in step with another far away, why a particle flying around a ring can live long enough to reveal its inner workings. As the wheels kiss the tarmac and the engines reverse, you have carried out the mildest of grand experiments and proven what the world's infrastructure quietly assumes. Fast motion trims the ledger of experienced time. Slow motion fattens it, and the universe, generous and exacting, honors both without contradiction. Step out into the jet bridge a few nanoseconds younger than you would have been had you stayed at the gate, and let the thought settle gently. Even ordinary travel is written in the ink of space-time, and part of learning to navigate a modern life is learning to respect the clocks that make that writing legible. Time crystals, order without flow. Imagine a material that ticks on its own schedule, not because it contains a hidden clock, but because the whole many-particle system settles into a rhythm that refuses to match the rhythm you drive it with. That is the strange promise of time crystals. Phases of matter that show order without flow, where the pattern repeats in time the way a crystal repeats in space. Yet no energy is being siphoned off to do work, and no perpetual motion is hiding in the walls. Start with something you already know. A spatial crystal, salt, quartz, ice, breaks the uniformity of space by arranging atoms into a repeating lattice, a pattern that stays put, even if the laws are the same at every location. A time crystal extends that idea into the temporal dimension, but with a crucial twist that keeps it honest. In the versions realized in laboratories today, the system is not asked to be magic at perfect rest. It is periodically driven, like tapping a swing or pulsing a microwave field. And in response, the whole system locks into a rhythm that is a clean multiple of the driving period. Most famously, period doubling. You drive it at once per beat, and the system replies once every 2 beats. And it does so rigidly, broadly, and persistently, even if you nudge the strength or timing a little. This refusal to dance on the metronome's beat is what physicists call discrete time translation symmetry breaking. The laws of the experiment repeat every pulse, but the state of the matter repeats only after 2 pulses. The first temptation is to think perpetual motion, but that misses the safety rail built into the setup. These are non-equilibrium phases. They keep their rhythm not by mining free energy, but by balancing drive and internal dynamics so that the system avoids heating into a featureless blur. 2 mechanisms make that possible. In one, called many-body localization, carefully arrange disorder pins excitations in place so energy from the drive cannot spread and melt the pattern. In another, called the pre-thermal route, a very fast drive corrals the system into a long-lived, almost conserved regime where heating is pushed far out in time. You still have a lifetime, but it can be astronomically long on experimental scales, long enough to call the pattern a phase rather than a fragile trick. Evidence that this is real and not a storytelling flourish comes from several platforms. Chains of trapped ions, charged atoms levitated and lined up by electromagnetic fields, can simulate spins that flip and nudge each other. When researchers pulse those interactions in a simple sequence, the spins answer at half the drive rate and keep answering that way for hundreds, sometimes thousands of cycles, even as imperfections are introduced. Defects in diamond known as nitrogen vacancy centers, tiny quantum magnets nestled in a carbon lattice, do the same under microwave driving and optical readout. The response is stubbornly locked to a subharmonic of the drive, not to some accidental resonance. Superconducting qubits on programmable chips, the kind used for quantum computing experiments, have also shown time crystal behavior. Tweak the driving steps, and the interacting qubits self-organize into a rhythm that stays put until you deliberately push the system out of its phase. Across these platforms, scientists look for 3 hallmarks before they use the phrase seriously. First, rigidity. The subharmonic oscillations don't wander with tiny changes in the pulse or the environment. They snap back like a pendulum at the bottom of its arc. Second, long-range order in time. The oscillations remain phase coherent over long stretches and across many degrees of freedom, not just in a single, carefully protected element. Third, insensitivity to fine-tuning. The behavior spans a region of settings rather than a razor-thin sweet spot. Meet those conditions, and you are not seeing a metronome accidentally synced to a harmonic. You are seeing the temporal analog of a crystal lattice, a pattern stabilized by collective behavior. There is an important boundary to keep you from being misled. Early on, a bold idea proposed that a true ground-state time crystal could spontaneously tick forever with no driving at all. Careful theorems showed that equilibrium systems can't do that without violating the logic that keeps thermodynamics sane. The modern story is more modest and more useful. Driven time crystals that break the symmetry of the drive itself, and related dissipative time crystals in open systems where the environment and pumping together stabilize a limit cycle. In that landscape, the phrase order without flow earns its meaning. No current is being harvested. No work is extracted. What is ordered is timing, the phase of a collective oscillation, protected by the same kind of robustness that makes a snowflake hold its shape. Once you accept that, practical and philosophical consequences open up. On the practical side, a time crystal is a frequency divider by nature. feed it a steady beat, and it outputs a locked, lower frequency that resists drift. That makes it a living testbed for precision metrology and for noise-resilient references inside quantum devices, because the subharmonic response can be more immune to certain errors than the bare drive. The same rigidity that keeps the pattern alive against jitter could be recruited to stabilize qubits, to bootstrap oscillators in chips where temperature and crosstalk would normally smear phases, or to sense tiny changes in fields and forces by watching how a robust rhythm detunes under a perturbation. On the conceptual side, time crystals force you to widen what you count as a phase of matter. Until recently, phases were mostly about equilibrium. Change the temperature or pressure and you glide from liquid to solid to gas. Here, the control knob is periodic driving, and the axes of the phase diagram include not just temperature and interaction strength, but drive frequency and amplitude. You can dial the system from a boring, synchronized state into a time crystalline regime, and on into chaotic responses, with sharp borders that look like phase transitions, even though the system never sits still. That provides a clean, empirical anchor for the intuition that the most interesting forms of order in nature may be inherently dynamical. Patterns not of positions, but of events, stabilized by feedback among many pieces. If your mind wants a picture you can hold without equations, imagine lining up metronomes on a wobbly table. If they were isolated and perfect, you'd force them to tick to your external tap. If the table lets them talk to each other, they can settle on a shared rhythm that isn't the one you impose. Make that table a quantum many-body system, make the tick a flip of a microscopic spin, and make the tap a train of pulses. The group can answer at halftime and keep doing so as small nudges come and go. Crucially, that survival of the rhythm is not the gift of a single pristine component, but of collectivity. Many imperfect parts holding a phase together in defiance of noise and drift. Will time crystals show up outside minimalist labs? We are already inching in that direction. Experiments are pushing to observe similar temporal order in magnon condensates, in exciton-polariton systems, and in driven cold atom gases arranged as lattices of light. Each platform brings a different trade-off: localization versus dissipation, isolation versus scalability, tunability versus stability. Wherever the balance lands, the diagnostic remains beautifully straightforward. Drive, watch for a rigid subharmonic, test its endurance, and map the region where it holds. If the pattern persists, you've captured order that lives in time rather than space. And here is the gentle closing thought that makes this more than a physics curio. You are used to thinking that steadiness in time requires a master clock and a quiet room. Time crystals suggest another route to reliability: consensus among many parts under a modest, regular push. A river does not need to be still to be predictable. A heart does not need to be motionless to be steady. A quantum material does not need to rest to show order. In a world where signals jitter, tools age, and environments refuse to be ideal, the ability to stabilize a beat by sharing it may prove as valuable as the ability to freeze a structure. Time crystals teach you to look for regularity, not only in what stands firm, but in what returns, again and again, on a schedule it chooses for itself. Quantum Zeno versus Anti-Zeno. Stare at a quantum system hard enough and you can freeze its change. Watch it a little differently and you can make it hurry. Two faces of the same deep rule known as the quantum Zeno and Anti-Zeno effects, which sound like a proverb about a pot that never boils, but are in fact precise, testable ways that measurement reshapes what can happen next. Begin with a clean picture. A quantum state left alone tends to evolve, often by slowly leaking from one configuration into another. An excited atom decays and emits light. A particle tunnels through a barrier. A superposition drifts in phase. For very short times, that leakage does not follow the familiar smooth curve you might expect. Instead, the probability of change grows only quadratically with time, meaning the very early evolution is fragile. If, during that fragile window, you perform rapid, sufficiently strong measurements that ask, "Are you still in the original state?" you repeatedly reset the clock on that early behavior, forcing the system to start its tiny departure from near zero again and again. Do this quickly enough, and the cumulative chance of leaving home stays small. You have created the quantum Zeno effect, a genuine laboratory-confirmed slowdown of decay or transition caused by observation itself. The idea moved from theory to practice when teams learned to count and disturb states without smashing them entirely. In one landmark experiment with trapped ions, researchers prepared atoms in an excited configuration and then peppered them with gentle, state-selective probes that would have flagged a transition. The more often they checked, the more the jumps were suppressed compared with runs where they left the ions alone. Similar demonstrations appeared in cold atoms held in optical lattices, where frequent "Are you here?" interrogations reduced tunneling across barriers, and in superconducting circuits, where repeated readout held a fragile state, steady longer than it would have survived in the dark. This freezing is not magic, and it is not free. Measurements disturb systems by design. Each query is a coupling that steals phase information or kicks the dynamics, and the effect only works when the measurement intervals are shorter than the characteristic timescale on which the system would otherwise commit to change. If you stretch the intervals or alter the kind of coupling, the story turns on its head. Past the tiny time regime, the environment, whatever bath of possibilities the system talks to, has a memory with its own preferred frequencies. Touch the system at a pace that resonates with those frequencies, and you can increase the rate of departure by opening more pathways for energy or information to flow. That is the Anti-Zeno effect, probing not as a brake, but as a catalyst. In carefully controlled experiments, physicists have watched tunneling speed up when they replaced rapid, projective checks with slower periodic kicks. In the language of spectroscopy, the measurement broadens the system's line and better matches it to the bath, making decay more likely. The switch between slowdown and speed up is not arbitrary. It depends on how the timing of your interventions overlaps with the environment's correlation time and with the spectrum of available transitions. If your monitoring is faster than the bath can blur the phase of the system, you carve out a protected subspace and trap the dynamics. If your kicks arrive in the regime where the bath can respond, you act like a person pushing a swing at the right moments. Each shove adds, and the motion grows. That unifying view replaces vague talk of observation changes reality with a concrete engineering knob. The rate and style of information you extract decides whether you lock behavior down or let it run. This is why the modern discussion emphasizes quantum Zeno dynamics, rather than only the stark freeze. Instead of asking the same yes-no question that pins the system to an initial state, you can ask a repeated question that constrains the system to move within a chosen subspace, like guiding a bead along a track by tapping it steadily from above. Experiments have used this to confine atoms to particular manifolds of motion, to implement logic gates protected by frequent checks, and to steer population flow in molecules in ways that hint at the eventual ability to sculpt chemical outcomes by timing light pulses as a form of measurement. On quantum computers, where the central headache is that fragile superpositions decay and pick up errors, Zeno ideas blend naturally with error correction. Rapid, gentle syndrome measurements keep unwanted transitions from developing fully, while the anti-Zeno regime warns that if you check too slowly or with the wrong coupling, you will only hasten the loss you hope to prevent. Even beyond computing, the pair of effects offers a new way to think about sensing. A detector that continuously monitors a field can freeze certain noise channels while amplifying others. By tuning the cadence, you choose which fluctuations your device ignores and which it highlights, the physical version of adjusting a camera's shutter to blur motion or to crisp it. Crucially, neither effect needs mystical language to feel astonishing. You can read it entirely as signal and bandwidth. Short-time quantum evolution starts with a flat slope, which is easy to interrupt by frequent questions. Longer-time behavior is sculpted by the spectrum of allowed exchanges, which you can either sidestep or excite depending on how you sample. That clarity has historical weight. Early arguments about whether a watched pot metaphor made sense were settled by concrete theorems and then by tabletop demonstrations with atoms, photons, and solid-state qubits. The gulf between philosophical puzzle and instrument setting has closed to the point where Zeno and Anti-Zeno are part of the practical vocabulary of modern labs. The remaining subtleties, strong projective measurements versus continuous weak monitoring, single systems versus many body ensembles, closed versus open dynamics, are precisely the levers that make the effects useful. A continuous, gentle readout can create Zeno-like stabilization without the harsh disruptions of stroboscopic checks, ideal for platforms where blasting the system would be worse than leaving it alone. Many body versions reveal collective slowdowns or speed-ups when interactions create new channels for energy to flow, open systems that exchange heat and information with a bath. Let us watch the crossover between regimes by simply changing the drive frequency or the measurement bandwidth. If you want a picture to carry without equations, imagine two musicians, one trying to hold a note, the other deciding whether to join. If the conductor taps the stand very rapidly, the player holding the note stays locked, counting too fast to drift, and the potential partner never quite finds the opening. Slow the taps to the tempo of the hall, and the resonance invites the second player in, and the music swells. Your taps are measurements, the hall's acoustics are the environment. The performers are the system's possible states. What begins as a parable ends as a prescription. To keep a fragile quantum note pure, tap fast and lightly. To coax a transition, tap in time with the room. And that brings us to a soft but pointed close. The Zeno and Anti-Zeno effects teach that in the quantum world, knowing is not neutral. It is a controlled interaction that can either fence off a possibility or open the gate. The difference lies not in a mystical observer, but in timing, coupling, and context. Variables you can measure, tune, and design around. You leave with two empowering questions. What exactly am I asking my system? And how often? And how does that cadence line up with the ways the world around it can answer? Ask them well, and you can make a pot that reliably refuses to boil. Or when you are ready, a kettle that sings on cue. Indefinite causal order. What if two events could be each other's before and after at the same time? Not because the world went lawless, but because at the smallest scales we can engineer, the order of operations becomes a property you can place into superposition and then read out like an interference pattern. This is the heart of indefinite causal order. A domain where you don't just ask whether A happens before B or B before A. You build a device in which both orders coexist until you look, and that coexistence can let you do things no fixed schedule can. The simplest doorway in is a thought device called a quantum switch. Imagine two black boxes, each transforming a quantum system in its own way. In ordinary life, you pick an order, send the system through box A and then box B, or reverse it. And those two routes generally produce different outcomes. The way washing then drying gives a different result than drying then washing. Now add a control qubit that can travel two paths at once, one path implementing A then B, the other B then A, and recombine them so the two histories interfere. As long as you don't ask too early which path the control took, the system behaves as if both causal orders are present, and the final pattern depends on their coherent mixture. This is not a verbal trick or a philosophical shrug. Laboratories have built optical versions where a photon's path acts as the control and its polarization is the workhorse being processed, and traption and microwave circuit versions where internal states play the same roles. In each case, when the apparatus is aligned and stable, you can verify a telltale signature called causal non-separability. No description that picks a single order at a time can explain the data, just as no classical picture of a single path can explain a double-slit interference fringe. From that foundation flow concrete advantages you can feel rather than merely admire. Suppose you are handed two mystery devices and asked whether they get along in a certain technical sense, whether their actions commute or anti-commute, using as few uses of the devices as possible. With any fixed order, you face a quota of queries that cannot be beaten. With a quantum switch, one call to each device inside an indefinite order can solve the same test with higher success, because the global phase accumulated by one order partly cancels or reinforces the phase from the other, and the interference writes the answer onto the control system like a clean yes/no. In other tasks, the advantage shows up as resilience. When the devices are noisy, A switch can pull a usable signal out of clutter that would drown it in any single order, letting you discriminate channels or align reference frames with fewer shots. There are communication gains as well. If two parties must send and process messages in a tight budget, fixed ordering imposes a ceiling on how well they can complete certain relational tasks. Allow the causal order itself to be controlled coherently, and you can beat that ceiling without sending more energy or more separate messages. What changes is the choreography of who influences whom. First, a resource in its own right. It is tempting to worry that this threatens the logic that keeps cause and effect sane, but the safety rails are firm. Indefinite order does not mean signals loop back in time to create contradictions. It means that at the level of operations inside a carefully isolated quantum network, the distinction between first and second is not settled until the control degree of freedom is measured. Once you read the control, or allow the environment to slurp away its phase information, a definite order emerges for that run, and the usual arrows of influence reappear with their ordinary discipline. The experiments are designed to make that boundary visible. Leave the control coherent, and you see interference between orders. Deliberately dephase it, and the advantage collapses, reducing the device to a mundane random choice between AB and BA with no special power. That dependence on coherence is how we know the effect is not a bookkeeping quirk, but a genuine operational resource. The practical horizon is wider than it first seems. In metrology, where you want to estimate a tiny parameter hiding in a transformation, indefinite order can amplify sensitivity by letting the unknown parameter imprint itself differently along the two causal branches and then subtracting the common noise at the recombination. In distributed quantum networks, a switch-like architecture could route fragile states through unreliable nodes in whichever order best cancels the specific noise that day, selected not by a scheduler, but by interference, which is faster than negotiation. Even in nascent ideas that flirt with gravity, researchers propose letting a single particle take two spatial paths that sit in slightly different gravitational potentials so that, from the particle's point of view, which happens first depends on which path you consider. Recombining those paths would then test whether nature tolerates superposed order beyond tabletop optics. Results so far are cautious and technical, but they share a strong theme. Order is not always a fixed backdrop. It can be a dial you turn. For a cleaner grip, trade the poetry for a rule of thumb. Whenever two operations do not trivially commute, the sequence in which you apply them matters. If you can create and maintain coherence between the possibilities A before B and B before A, you can harvest interference terms that any classical mixture of the two would wash out. Those terms are where the advantage lives. They are also where the fragility lives, because stray noise that distinguishes the two routes, vibrations, timing jitter, path length mismatch, acts like a nosy observer, marking which order occurred and spoiling the effect. This is why demonstrations emphasize stability, and why the first real applications may appear in niches that already demand quiet environments, such as quantum sensing labs or error-protected subroutines inside processors rather than street corner gadgets. Still, the conceptual payoff arrives immediately and costs nothing to carry into your day. We grow up treating order as a given. Wake then work, cause then effect, instruction then outcome. Indefinite causal order invites you to hold a softer idea. Sequence can be engineered, and under the right rules, engineered sequence can be superposed. That does not license sloppy thinking. On the contrary, it asks for precision about what is being ordered, about where coherence is kept, and about when the world is allowed to learn which happened first. It also invites healthy doubt toward claims that blur it with time travel or mind over matter narratives. Nothing here overturns the causal structure that keeps signals flowing forward in every local frame. What changes is our inventory of resources. Alongside energy, information, and entanglement, we add causal structure as something we can manipulate. The closing reflection is gentle but pointed. Progress in understanding often comes not from discovering a new substance, but from noticing that a familiar distinction, here, before versus after, can be treated as a quantum degree of freedom. When you do that with care, you gain leverage, sharper tests, thriftier protocols, and a fresh angle on how agency and sequence braid together at the edge of the possible. Indefinite causal order is not a license to break cause and effect. It is a blueprint for bending the scaffolding of order just enough to let interference work for you, turning the grammar of processes into another instrument on the bench, and quietly, into another reason to be humble about how much of the way things must be is really just the way we have always arranged them. Two-state vector formalism intuition. Imagine reading a mystery from both ends. One thread begins at the crime scene and moves forward. The other starts at the confession and moves backward. And only when the two threads meet do the clues in the middle make full sense. That is the everyday intuition behind the two-state vector formalism, a time-symmetric way of looking at quantum experiments where you describe a system not only by how it was prepared, but also by how it is later found. And you let both boundary conditions illuminate the strange events in between. Start with what you already trust. In most labs, you prepare a photon, atom, or qubit in a known condition, and then you measure it at the end, reporting the outcome. TSVF asks you to treat both steps as real pieces of information, and to use them together when you talk about the system in the middle interval. You still obey ordinary quantum rules, no faster than light messages, no contradictions. But you allow yourself a richer bookkeeping, a forward-evolving state that carries what you know from the past, and a backward-evolving state that carries what you know from the future measurement. When those two meet in the middle, they shape the probabilities you assign to gentle, non-disruptive probes called weak measurements, which are the formalism's practical lens. You touch the system so lightly that a single trial tells you almost nothing, but many repeated trials reveal a tiny average shift, a needle nudge that exposes how the forward and backward stories overlap. In that regime, you encounter the notorious weak value, a number that can sit outside the range you'd expect from strong projective measurements. Rather than magic, this is interference made legible by statistics. The same way a whisper repeated 1,000,000 times becomes a clear word. Here's how to fit it into your intuition without drowning in equations. Imagine a playing card hidden under one of 3 cups, and imagine you're promised that at the end you'll peek and only keep the runs where the card is, say under cup C. TSVF says that in the middle you should talk about the card using 2 facts, the way you shuffled at the start and the way you filtered at the end, and that certain carefully designed, almost non-invasive questions asked mid-game can return averages that reflect both constraints at once. That's why some counterintuitive 3-box experiments report that, conditioned on a particular final find, the card leaves telltale traces as if it was strongly associated with 2 places at once. The traces are weak, statistical, and only show up after you collect many trials. But they reveal a consistent pattern. The middle of a quantum story can be sharpened by the ending you select. Not by rewriting history, but by talking precisely about the sub-ensemble of runs you kept. The payoff of this perspective is more than a puzzle. It gives you a disciplined language for retrodiction, the art of reasoning backward, without cheating. In standard forward-only talk, you predict distributions and then shrug at the specific run you got. In the two-state view, once the outcome is known, you update your description of the past with the same seriousness you would use when updating beliefs in everyday life. Learning the answer changes what you think the hints meant. Weak measurements keep you honest by forcing you to gather evidence without bulldozing the system, and by making you average over many runs so that lucky noise doesn't masquerade as structure. Along the way, you learn why those famous anomalous weak values matter and where they do not. They matter for metrology because they can amplify tiny effects into larger pointer shifts when used carefully, making it easier to detect a small deflection or phase without saturating your detector. They do not give you free energy or perfect precision, because the amplification usually comes at the price of throwing away a lot of data through strict post-selection and by increasing technical demands on stability. They matter for foundations because they let you map which-way type influences in delicate interferometers without collapsing the very interference you want to study, offering a controlled way to talk about path-dependent effects. They do not license sensational claims about violating causality, because the post-selection filter is applied only when all the data have already been recorded, and no signal can be sent backward by deciding later which records to keep. This is the right place to place guardrails for your own thinking. TSVF does not change outcomes. It reorganizes your description of the ensemble so that both past preparation and future selection appear explicitly in the middle time bookkeeping, and its empirical bite comes only when you use measurement settings that are gentle enough to preserve coherence across many trials. When you look at the experimental record, you find a steady pattern rather than fireworks. Optical interferometers, where single photons experience two operations in different arms, and weak probes read out path-dependent shifts conditioned on a final detector click. Solid-state qubits, where gentle couplings to read out resonators reveal state-dependent phase nudges that match two-state predictions. Atomic ensembles where polarization rotations too small to see in one pass are recovered by post-selecting on a later outcome and averaging a vast number of runs. In each case, if you remove the post-selection, the anomaly washes away as expected, because you are back to describing the full, unfiltered ensemble with a single forward story. Seen this way, the formalism stops being mysterious and becomes a kind of optical device for thought, a way to bring the initial and final boundaries into focus so that the faint patterns in the middle pop out of the background. What do you gain by carrying this lens into your own learning? First, a cleaner sense of how conditions shape meaning. You learn to ask, conditioned on what? Before you trust an average, which is a scientific habit that pays dividends far beyond quantum physics. Second, a respect for the difference between exploring without breaking and interrogating to decide. Weak measurements are the first. Strong measurements are the second, and both are necessary, but confusing them leads to myths about seeing the impossible. Third, a new humility about narratives. The story that best explains mid-course evidence can change when the ending changes. And acknowledging that is not weakness, it is intellectual honesty. If you are tempted to stretch the lesson into life, do it gently. You can't post-select your biography, but you can revisit earlier clues once an outcome is known and let that revise your understanding without pretending the past changed. And if you want a tangible, practical takeaway for technology, it is this. Time-symmetric descriptions help engineers design control and read out sequences that are optimized not only for what they inject at the start, but also for how they intend to filter at the end, which can reduce noise, sharpen parameter estimates, and protect fragile quantum states in the middle. At the soft closing of this idea, let the metaphor of the two-ended mystery return. A story told only forward leaves some clues looking like noise. A story told only backward leaves motives looking like fate. A story told with both boundaries in view reveals why the footprints in the middle are where they are. That is the intuition of the two-state vector formalism you can keep without memorizing symbols. A disciplined way to say that in quantum experiments, beginnings and endings are both facts, and the gentlest truths live in the narrow, careful space where those facts meet. Page Wootters, Time from Entanglement. Picture a universe that never ticks, and yet everything inside it moves. That is the gentle shock of the Page Wootters idea. What if time is not a global river flowing for all things at once, but a pattern that appears when part of the world is used as a clock for the rest? So that motion is real relative to that clock, even if, from the outside, the entire universe sits in a perfectly still quantum state. Begin with the puzzle that motivates this view. When you try to write down the state of the whole cosmos, using our best merger of gravity and quantum rules, you don't get an equation that says the wave of the universe changes with time. You get a constraint that says the total energy is balanced so precisely that the whole thing looks stationary. A frozen universe sounds wrong, only if you assume time must be an external backdrop. Page and Wootters invite you to drop that assumption and look inside. Choose a small, well-behaved part of the world to act as a clock. Perhaps a qubit that can point to a handful of phases, or an atom whose internal levels can be read like a hand on a dial, and then entangle that clock with a system you want to watch. Prepare them together so that each possible reading of the clock is paired with a matching state of the system, and tune the global state so carefully that, as a whole, it satisfies the timeless constraint. Now do a subtle thing. Ask questions only of the form, what is the system like when the clock reads this particular value? Conditioned in that way, you find that the system's states, seen step by internal step, line up exactly like the usual evolution you were expecting all along. The same sequence you'd write for a particle spreading, a spin precessing, or a field oscillating under standard dynamics. What looked static from the God's eye view becomes a moving story from the perspective of an embedded observer who consults the clock and compares notes. This is not wordplay. It has been turned into tabletop reality with carefully entangled photons and other platforms that simulate the logic. An external analyst who refuses to read the clock sees an unchanging joint state, while an internal analyst who conditions on a clock reading reconstructs the ordinary movie of change. The key insight is that correlation plays the role we usually assign to an external time axis. The clock's record and the system's record are knotted together, so that asking about one at a given reading gives you a crisp answer about the other. And the pattern of those pairings is the flow we call time. This perspective immediately explains why an ultimate, all in view, can be timeless, while local life is full of rhythm, memory, and cause. Within the correlations, subsystems can carry histories that agree with the laws, even though there is no extra metronome outside the whole. It also reframes what a good clock must do. A practical clock is not a mystic oracle. It is a device that has a long train of well-distinguished states you can query without wrecking it. Couples to the rest of the world weakly enough to keep good time, but strongly enough to share correlations you can actually read, and accumulates only manageable noise as it runs. Those mundane demands hide deep constraints. Measuring a clock inevitably disturbs it a little. Isolating it perfectly makes it useless. And the more finely you try to resolve its ticks, the more energy and fragility you import. Hints of fundamental trade-offs that echo in quantum limits for measuring durations and in precision metrology. The Page-Wootters lens makes those trade-offs feel natural rather than frustrating, because it says the clock is not a spectator, but a partner. Every bit of accuracy you demand is paid for by tighter and more delicate entanglement with what you're timing. From there, the idea ripples outward into places you can use it. In quantum control, engineers already introduce clock qubits or oscillator modes that pace a computation. The relational view clarifies why synchronizing these to the data qubits is not just a convenience, but the essence of keeping a coherent narrative in the device. In sensing, you can treat a field or force as something that perturbs the correlation between a clock and a probe, turning drift in their relationship into a signal. This is, in spirit, how modern atomic clocks and interferometers harvest information from minuscule phase shifts. In Foundations, the framework gives a clean way to talk about observers who are part of the universe they measure. An external auditor who refuses to read any internal clocks may say, nothing changes. But any observer who ties their experiences to a physical clock inside will recover a consistent, testable arrow of happenings. And yes, there is an arrow. The Page-Wootters story by itself is time-symmetric, but when you add realistic environments and let the clock and system leak information into countless idle degrees of freedom, you get records that are easy to write and hard to rewrite. Entropy increases because the correlations disperse into places you will never coordinate again, and the direction in which records accumulate becomes the direction you call future. This view also cures certain confusions. It prevents you from hunting for a single, universal now spread over the cosmos, because when always means relative to this clock. It keeps you honest about the difference between prediction and retrodiction. Once you have read an outcome, you are authorized to update your description of past correlations, just as you would in any careful inference problem, without pretending that the outcome traveled back to rewrite events, and it warns you about sloppy talk of perfection. No clock can have infinitely sharp ticks, because perfect sharpness would require infinite resources and would destroy the very correlations that define time in the first place. If you want a picture that needs no equations, imagine an enormous library in darkness. Each shelf has pairs of books bound together by a ribbon, one book labeled clock, the other world. To an outsider who never opens a volume, the library is quiet and still. a timeless archive. But a reader who sits at a table and opens pairs in order discovers a story. As the clock pages advance, the world pages tell of leaves fluttering, rivers widening, people speaking. The story exists in the pairings. Without reading the clock books, the world books are a jumble. And without the world books, the clock books are empty numbers. That is the soft heart of page Wootters. And the closing comfort is practical. You don't have to choose between a frozen absolute and a flowing absolute. You can live with a relational truth that matches both your instruments and your intuition. Time is what good correlations look like from the inside. Build better clocks and better ways to read them, and your slice of the universe becomes more orderly, more predictable, and more beautiful. Not because a cosmic second-hand sped up, but because the ribbons tying you to what you watch were woven with care. Quantum speed limits on change. Try to flip a quantum coin from heads to tails as fast as you can, and you collide with a boundary that isn't about your engineering patience, but about nature's budget. There is a minimum time any system needs to become meaningfully different from what it was. A hard floor known as a quantum speed limit. And once you see it, you start to recognize the same kind of budget everywhere. From how quickly a qubit can perform a logic gate to how rapidly a tiny engine can extract work without stalling. The cleanest way to feel this limit is to imagine distance not in meters, but in distinguishability. At the start, a system sits in a well-defined condition. After some evolution, you ask how far it has moved in the space of possibilities, with far meaning easy to tell apart. To get from indistinguishable from the start to as different as possible, the dynamics must pay with a resource, and that resource is tied to energy, specifically to how widely the system's energy components are spread and how much average energy above the baseline you're investing. Spread the energy too little and the state barely budges. Invest more and it can tilt faster along the shortest available path. This is why a fast quantum gate on a qubit is not simply a matter of hammering harder. The fastest route corresponds to a clean, tight swing along a great circle in its state space. And the time to complete that swing shrinks only insofar as you can marshal energy in a controlled way. Beyond that, extra brute force stops helping and starts causing leakage into states you didn't intend, turning speed into error. The remarkable thing is that researchers have made these ideas exact without drowning you in symbols. There are crisp statements that bind the minimum transformation, time to two intuitive quantities: one, capturing the spread of energies available to the state, the other, capturing the height of energy you've put at its disposal, so that for a given goal, you can compute a floor below which no protocol can go. If you try to cheat by using complicated, time-varying pulses, the floor follows you. If you switch to a different physical platform, the floor re-expresses itself in that platform's language but does not vanish. If you couple your device to an environment, the limit changes, but it persists, because now the relevant energy scales include the way the surroundings drain or jostle your system while it tries to move. This is where the notion becomes practical rather than poetic. In quantum control, the speed limit serves as a ruler for your ambitions. If your target gate time hovers only a hair above the limit for the available energy and coupling strengths, you know you are operating in a regime where small imperfections will push you into the red. Dialing the target just a little slower buys a lot of robustness. The way driving just under the traction limit keeps you on the road through a turn. In precision sensing, the same logic flips sign. To resolve a weak effect quickly, you want to boost the relevant energy spread in your probe so that the state can separate faster from its initial condition and write a readable signal in less time. But because total energy and fragility tend to rise together, you face a trade-off that the speed limit makes explicit. In quantum thermodynamics, tiny engines and refrigerators made from a few levels each can be asked to deliver work fast. But as you push the cycle period down toward the limit set by their gaps and couplings, dissipation spikes and output collapses. There is no shortcut to arbitrarily quick usefulness. The same budget thinking has reached quantum batteries, a playful name for arrays that store energy in many body states. Clever interactions can speed collective charging, but the laws still draw a line between faster, because cooperative, and impossible because the minimum time for a given energy input has been hit. Even the way we talk about the maximum rate of computation, in abstract models that ignore all the mess of real hardware, carries the echo of a speed limit. If each elementary operation must cross a finite distance in distinguishability space, and each crossing requires a finite time for a given energy, there is an ultimate ceiling on how many reliable flips any physical computer can do per unit. Time per unit energy. With this map in mind, the design playbook gets richer. One route to faster change is to steer along the shortest path in state space, the geodesic, rather than flailing with detours. In practice, this means shaping control pulses so that the system never drifts into needless corners of its possibility space. Another is to use shortcuts to adiabaticity, protocols that mimic a slow, careful transformation in a fraction of the time by adding just the right extra hand to guide the system along without exciting unwanted modes. Here again, the speed limit is not broken, but approached gently by spending the necessary energy in a targeted way rather than as heat. In open systems, where noise is inevitable, the speed limit acquires a new diagnostic role. By measuring how quickly a state moves away from itself under the combined push of your control and the pull of the environment, you can back out effective rates and identify whether you are in a regime where coherence can be harnessed or where you are simply stirring soup. This saves time in the lab. If your observed evolution time is already just above the bound for your platform, hunting for a tenfold speed-up is fantasy. If your time is far above the bound, you have headroom and should search for a better control path or a better partition of energy across the steps. It helps to hold a picture in your head that needs no formulas. Imagine each quantum task as a trip across a curved landscape where distance means how different the destination is from the origin. You are given a fuel allowance that translates into 2 dials, how widely you can spread your engine's available energies and how high above idle you can run it. The shortest time trip snakes along a ridge that stays just risky enough to be direct, but not so risky that you slide into a ravine of errors. Try to sprint without enough grip and you tumble. Crawl too cautiously and you waste daylight. The speed limit is the mountain's grade, a property of the terrain, not just your shoes. And because it is a property of the terrain, it also carries a philosophical kindness that keeps you from confusing impatience with insight. When a device will not go faster despite your best design, the right question is often not, what trick am I missing? But what resource am I refusing to pay? More coupling strength, better isolation to allow a higher energy spread without leaks, a different encoding that shortens the geodesic, or a revised target that achieves the spirit of the task with a smaller distance to cover. Seeing the world that way invites honest conversations about limits in other arenas too. How quickly a sensor can settle before a decision must be made. How rapidly an error-correcting code can heal before noise overwhelms it. How fast a distributed network can synchronize without tearing itself apart. The soft closing thought is this: speed in the quantum world is not a matter of stomping on an invisible pedal. It is a choreography between distance, resources, and risk. The laws do not taunt you with unreachable possibilities. They trace a line on the floor and say, here is what can be done cleanly. Learn to read that line, and you stop wasting effort on mirages. You start building protocols that move as fast as truth allows, no faster, and, most importantly, no slower than you need. Pauli's no-time operator, puzzle. Suppose you tried to build a time meter for a single quantum system, the way you build a ruler for position or a dial for spin. One neat operator you could point to and say, this is time. And then discovered a stubborn brick wall. Under very general and physically reasonable conditions, there is no such operator. A puzzle crystallized by Wolfgang Pauli and now nicknamed the no-time operator problem, which forces you to rethink what you mean by time in quantum theory and why experiments that obviously measure times do not contradict the theorem. The hook is simple but biting. In the usual quantum toolkit, observable quantities are represented by operators, and certain pairs, like position and momentum, come as conjugates, linked by a deep kinematic tension that shows up as uncertainty and interference. It's tempting to treat time and energy the same way. to promote time from a backdrop to an observable on equal footing with energy. Pauli noted that if you insisted on a genuine, self-contained time operator that plays the same canonical role with energy as position does with momentum, meaning that acting with the operator would march a state forward or backward in time, just as the momentum operator shifts position, then the energy spectrum would have to run from negative infinity to positive infinity with no lower bound. That is not what the physical world gives you. Most Hamiltonians have a flaw because there is a state you call ground, and you cannot go below it without tearing reality. That mismatch is the heart of Pauli's objection, and it is more than pedantry, because a system with no ground would be unstable, bleeding energy forever. The conclusion many took for decades was stark. Time is a parameter that labels change, not an observable to be read off a single system operator in the same way as position, and the effort to force it into that mold leads to unphysical consequences. Yet the puzzle is not the last word. It is the first sane constraint you meet on a more careful road. The first step on that road is to separate two very different questions that everyday language tends to blur. One question is, does the theory have a single universal time operator that you can measure to learn what time it is for an isolated system? To which Pauli's argument says no under broad conditions. The other question is, can you build devices that report physically meaningful times of arrival, of flight, of waiting, of decay? And can the theory describe those reports? To which the answer is emphatically yes, but with a different mathematical accent. The accent is this. Many time quantities are not represented by sharp, self-adjoint operators with tidy spectra. Instead, they live as measurements defined by procedures, formalized as positive operator-valued measures, or as specialized constructions whose statistics reproduce what stopwatches read when you run a concrete protocol. Think of a time of arrival experiment. You prepare a particle, let it move toward a boundary, and fire a detector that clicks if and when the particle gets there. The distribution of click times is an observable phenomenon, stable under repetition and calibration, but it is coded by an operational rule, rather than by the spectrum of a single arrival time operator that would be conjugate to the Hamiltonian for all systems. This subtle shift from operator equals quantity to measurement procedure equals quantity sounds like a technicality, but it is the exact seam where the theory meets the lab, and it rescues our ordinary talk about lifetimes, dwell times, tunneling times, and coherence times from being illegal. Another way to see the sanity of Pauli's barrier is to ask what you would demand of a true time operator if one existed. You would want it to translate states the way a hands-on clock does. Tick forward, and the state evolves under the Hamiltonian. Tick backward and it unwinds. Repeat this indefinitely, and you are effectively sweeping energy across all values, as if energy had no flaw. That's fine for purely mathematical toys, or for systems with periodic energy that you treat as a rotor, but it clashes with the stability of real matter. The right moral, therefore, is not give up on time, but match the notion of time to the structure of the system. For bound systems with a well-defined ground and a discrete ladder of energies, time behaves more like phase on a circle than like a straight coordinate. You can meaningfully talk about relative phases that advance, about waiting times between events, about periodicities encoded in correlation functions. But you should not expect a global time operator that ticks through all reals any more than you expect a global angle operator that is perfectly sharp and unbounded. In scattering systems and flight problems, where the Hamiltonian supports traveling states, you can recover time of arrival constructs that work superbly well. But they are built from the dynamics and boundary conditions of the task at hand, not from a one-size-fits-all conjugate. This is why the energy-time uncertainty relation must be understood with care. Unlike the position-momentum case, it does not refer to the variances of two operators you could, in principle, measure on the same footing. Instead, it encodes trade-offs between how sharply you prepare energy and how quickly a state can demonstrate change, or between the line width of an unstable state and its lifetime. Statements about evolution and bandwidth, not about two knobs on the same instrument. Once you see this, a lot of confusions evaporate. It becomes clear why atomic clocks, which are the most precise timekeepers we have, do not measure time directly. They measure frequency. the rate of a phase advance in a carefully engineered transition, and then count cycles against a standard. Time emerges as a tally of coherent oscillations locked to a procedure and a calibration chain that ties your lab to international standards. The clock's accuracy is a triumph of controlling energy differences and environmental couplings, not of exposing a hidden time operator. It also becomes clear why experiments on decay times, tunneling delays, and transport lags yield sensible numbers without breaking Pauli's rule. Each number refers to a protocol, a way of preparing, evolving, coupling to a detector, and sorting outcomes. And the theory predicts the distribution of reported times using dynamics and detection models, again with no need for a universal T observable conjugate to every H. If you push further, the puzzle even helps you design better measurements. When you cannot rely on a single operator, you are forced to make your definitions operational and to map which features of dynamics your stopwatch truly samples. In practice, this breeds metrological honesty. For example, the arrival time you infer by the first click of an absorbing boundary is not the same as the passage time through a region inferred by adding and removing weak scatterers. Both are legitimate, both have calculable distributions, and both teach you different things about motion and interaction. It also reminds you that incorporating the timing device into the quantum description is not optional. A good quantum timer is itself a system with states, couplings, and noise, and you will only extract reliable times if you design it to trade minimal disturbance for readable records. Exactly how modern ultra-fast experiments balance weak pointer shifts with large data sets to reconstruct when events most likely happened without smashing the very coherence they want to study. Perhaps the most liberating lesson arrives when you return to the big philosophical picture. We are used to thinking of time as an external river, that everything drifts down at the same rate. Pauli's puzzle tells you that in the quantum language we actually use, time enters through how systems change and how we register that change, not through a universal needle that every isolated particle carries inside. That shift does not demote time, it situates it. It says, if you want to talk about what time is it for this process, bring along the process that plays the role of a clock and the protocol that ties the two together. In turn, this relational posture fits the world you live in. Trains run on schedules because clocks are synchronized by exchanging signals. Laboratories synchronize oscillators by comparing phases over fibers and satellites. Your phone's time is a consensus forged by devices that never share a single operator, but do share a network of procedures and corrections. In a quiet way, Pauli's brick wall has kept physics honest for nearly a century by blocking a tempting but misleading shortcut. It forces us to earn every time statement by naming the mechanism that produced it. The soft closing thought is this: the absence of a universal time operator is not a hole in the theory. It is a signpost pointing to where the meaning of time actually lives, in dynamics, in correlations, and in the instruments we craft to witness them. Accept that, and your understanding becomes both humbler and stronger. Humbler, because you stop expecting a single dial to settle every timing question. Stronger, because you can now design, interpret, and trust time measurements that arise from clear, physical procedures, exactly the way good science should. Ramsey clocks and phase ticks. If you want to understand how the best clocks on Earth count time without staring at a moving hand, imagine teaching atoms to listen for a beat they already carry and then asking them, very gently, whether your reference is in step. This is the Ramsey method, the quiet heart of modern timekeeping, where phase ticks, rather than mechanical ticks, tell you if your oscillator is running fast, slow, or perfectly true. The choreography looks simple from far away. You prepare an atom with two long-lived internal levels that can act like a tiny compass hand. You give it a brief, carefully tuned burst of electromagnetic light that sets the hand halfway between up and down so it can feel and remember phase. Then you let it drift in silence for a chosen wait, during which the atom's own natural rhythm advances like a metronome buried inside it. Finally, you deliver a second brief burst and read out how the hand lands. If your laboratory oscillator matches the atom's natural frequency, the two bursts add up just so, and the population falls one way. If your lab source is off by a whisper, the accumulated phase during the quiet period rotates the hand before the second burst arrives, and the readout swings the other way. Walking the wait time and repeating this sequence paints a fringe pattern, bright and dark bands of outcomes, that behaves like an interferometer in time. The narrower the bands, the more finely you can tell whether you are on tune. That is the Ramsey miracle in plain terms. By splitting one long question about frequency into two short questions with a period of listening between them, you trade raw power for discrimination, the way a violinist uses two light taps and the echo of the hall to judge pitch more exquisitely than a single heavy strike ever could. Under that grace lies a stack of choices that turn phase into honest seconds. First is the transition you choose to anchor your clock. Microwave hyperfine flips in cesium or rubidium for traditional primary standards, or far higher frequency optical lines in elements like strontium, ytterbium, and aluminum for the latest optical lattice clocks that divide a second into hundreds of trillions of ticks. Optical transitions are attractive because more ticks per second mean more chances to average down noise, but they demand lasers that are absurdly stable. Laboratories tame them with ultra-quiet cavities carved from low-expansion materials, mirror coatings that barely dissipate heat, and sometimes cryogenic housings to quiet thermal jitter. Second is where you keep your atoms while they listen. Fountain clocks toss cesium upward in a vacuum, so the atoms spend longer in free flight between bursts, shrinking the width of the Ramsey fringe. Optical lattice clocks trap thousands of neutral atoms at the magic wavelength, where the trap's light shifts both levels equally, so the holding potential doesn't spoil the tick. Single ion clocks pin one atomic ion in place with electromagnetic fields, trading sample size for exquisite control over motion and environment. Third is how you fight the world's attempts to bias your reading. Blackbody radiation from room temperature walls nudges energy levels. Stray magnetic fields tip phases. Collisions between atoms slightly retune the line. And even the probing light itself can push the transition off target. So clock teams measure in alternating conditions that flip the sign of each suspected shift and then average, or they engineer the geometry and polarization of light to cancel the most dangerous drifts. The Ramsey sequence becomes a Swiss army knife for all this. By changing the wait time, the symmetry of the pulses and the relative phases, you can make the clock sensitive to what you care about and blind to what you don't, like tuning a microphone to catch a voice in a windy room. Then there is the quiet villain you never see. The local oscillator that drives your pulses brings its own phase noise, and because you sample the atoms only during the short bursts and not during the entire cycle, that noise is partly aliased into your measurement, a practical limitation known in the field as the Dick effect. Engineers push it back with longer interrogation times that reduce sampling gaps, with synchronous comparison of two clocks so common noise cancels, and with correlation tricks that let two ensembles listen to one laser at the same time and subtract its wanderings. On the quantum side, another limit shows up as projection noise, the unavoidable jitter in outcomes when you measure many identical atoms that were prepared in a superposition. The fractional uncertainty after one shot scales like 1 over the square root of the number of atoms, which is why lattice clocks love large ensembles. But even this ceiling is not absolute. By entangling atoms into spin-squeeze states, you can reduce the jitter and further sharpen the phase readout. A demonstration that the same quantum effects that usually threaten coherence can be recruited to improve it when handled carefully. All of these details remain anchored to one idea that is simple enough to carry without symbols. Phase is your currency. The two Ramsey bursts frame a window in which the atom's phase advances at its private rate. Your job is to compare that phase to your lab's carrier without disturbing the very advance you want to witness. Push the wait time longer, and you amplify tiny frequency errors into large, easy-to-see phase shifts. But you must protect coherence the whole way. Increase the number of atoms, and your average becomes cleaner. But you must fend off collisions and shifts due to density. Shorten the pulses, and you reduce how much your own probing disturbs the atom. But you must ensure they still set the compass hand cleanly. Each knob trades one kind of uncertainty for another. And the art of a good clock is to find the sweet point where all the nuisances cancel down more quickly than the seconds accumulate. Why does this matter beyond the romance of perfect time? Because phase-tick truth is now a metrological language that spills into everything that needs steadiness and sensitivity. Networks that synchronize telescopes on different continents rely on Ramsey-like comparisons to keep their stations in lockstep. Gravity experiments weigh tiny differences in potential by watching frequency shifts in clocks just centimeters apart. Secure communications and navigation ride on carriers whose phase drift is policed by atomic references. Even attempts to test whether fundamental constants drift over years and decades boil down to long, patient Ramsey interrogations of different elements, looking for mismatched phase stories that would betray a slow change in nature's numbers. And there is an everyday wisdom hidden in the technique that anyone can use. When a problem demands precision, there is power in pausing to listen between two light touches instead of hammering once and hoping. The pause is where the world tells you how it would like to be measured. So when you hear that the most accurate devices we have do not watch a hand sweep but read a fringe of phase, trust that simplicity. 2 gentle questions, a period of silence, and an honest comparison are enough to keep our civilization's heartbeat steady. The final comfort is soft but real. A good Ramsey clock doesn't make time. It makes agreement about time by letting atoms do what they do best and by turning their phase into a universal meeting point. In a noisy universe, that may be the most beautiful tick of all. Gravitational potential and clocks. Set a clock on a shoreline rock and another in a mountain observatory. Then ask a quiet, radical question. Which one lives higher in the Earth's energy landscape? And how would you know without a tape measure? Because the honest answer is that clocks themselves reveal height by how fast they tick, not in steps but in potential. And learning to read that potential turns timekeeping into a way of weighing the world. Gravity is not just a downward tug. It is a map of how costly it is, energy-wise, to sit here rather than there. And every physical rhythm, an atom's internal beat, a crystal's whispering resonance, pays that cost, running a hair slower deeper in the map and a hair faster higher up. What makes this more than a slogan is the way modern clocks have crossed from good to sensitive. Optical clocks that count hundreds of trillions of phase cycles per second can now tell when you lift them by the height of a book. And they do it not by watching a hand sweep, but by comparing their phase stories. Place 2 of them at different potentials. Link them by a quiet optical fiber, and you see a fixed offset in their rates that is as reproducible as sunrise. The shift doesn't care whether a mountain made the potential high or the ocean floor made it low. The clock feels the total geopotential, including Earth's rotation, so that the surface we call mean sea level, more precisely, the geoed, is not a flat plane, but a lumpy equipotential shell. And ideal, well-corrected clocks resting on that shell and co-moving with the ground would agree on their pace, even though some sit at different geometric altitudes. This is the seed of a new craft with a lyrical name, chronometric geodesy, where surveyors trade leveling staffs for frequency ratios and draw height differences directly from time, watching how the planet's mass distribution sculpts the rate of change itself. Push on that idea and the world opens. When heavy winter storms load the atmosphere over a region, the extra air mass deepens the local potential, just enough to slow a clock by a measurable sliver. When groundwater basins are pumped down or refill after rains, the missing or returning weight tugs the potential and the clock's rate follows. When a magma body swells under a volcano, clocks ring a faint alarm, not by shaking but by noticing the new gravitational burden. Even the tides leave their signature, twice daily, as the moon and sun rearrange Earth's potential, and every disciplined oscillator on the surface breathes in time with a celestial rhythm it cannot ignore. Because these signals are small, honesty about noise and method matters. Linking clocks over tens to hundreds of kilometers demands optical frequency combs that translate one color's purity into another, phase-stabilized fibers that cancel the jitter picked up over the route, and careful accounting for everything that pulls on frequency. Temperature gradients, magnetic fields, stray collisions in the atomic ensemble, even the faint radiation from room temperature walls. Once those nuisances are tamed, the remaining offsets are not mistakes. They are measurements of where on the potential map each clock stands, and stitching them together yields contour lines of clock height that complement satellite gravimetry and classic leveling, often with less drift over time, because a clock's reference is universal physics rather than an evolving benchmark. The metrology community already lives with this reality every day. To keep the world's official timescale coherent, national labs report their clock's frequencies with corrections for their station's potential, so that a standard in a valley does not quietly disagree with one on a plateau. Without that honesty, the grand average we all set our phones by would slowly warp as participants sit at different depths in Earth's field. The same discipline keeps navigation sane at planetary scale. When you compare signals from devices in different orbits or on different ground stations, the rate offsets due to potential must be applied, or distance estimates drift and the map unthreads. What is new is not the principle, but the reach. Optical clocks have made the correction big enough, instrumentally speaking, to be a tool rather than a footnote. That tool has surprising range. In fundamental physics, clock networks test a principle called local position invariance, the statement that non-gravitational physics is the same no matter where you are. If some new field or subtle departure from Einstein's rules tilted the potential dependence differently for different atoms, a cross-comparison of clock species spread across a continent would see the mismatch. In Earth science, arrays of clocks could watch glaciers lose mass, deltas subside and aquifers fill or empty, providing a time-based complement to GPS positions and satellite gravimetry that is less sensitive to local ground motion because it asks, how deep in the potential well is this point, rather than how high above a reference surface does it sit. In coastal cities, such arrays might one day support sea level adaptation not only by tracking the waterline, but by measuring the changing weight of the ocean itself as it sloshes under shifting winds and currents. And there is a modest but beautiful practical wisdom hiding in the details. Because gravitational potential is a global property of the mass distribution, two places with the same local gravity, the force you feel, can still sit at different potentials and therefore run clocks at different rates. Force is about the slope of the landscape. Potential is about the altitude on that landscape, and clocks are altimeters, not spring scales. That distinction resolves confusions that trip up even careful readers. A strong local field on a steep mountain doesn't guarantee a slower clock than a gentler field near sea level, because what sets the tempo is depth in the well, not steepness of the wall at your feet. It also explains a quiet fact about our spinning planet that often sounds paradoxical. Although rotation makes the equator bulge and changes both the centrifugal contribution and the underlying gravity, clocks that share the same geopotential surface, once you account for the motion that comes with being on a turning Earth, keep pace with one another. Which is why mean sea level is such a powerful concept for synchronizing reality. None of this invites magical thinking. It invites careful design. To use clocks as potential meters, you must nurture coherence, the ability of atoms to keep a faithful phase story over long interrogations. You must learn your instrument's biases so thoroughly that the only remaining shift is the one the planet wrote. And you must build comparison links, fiber on land, free space or satellite paths across oceans that do not smuggle in excess noise. What you get for that craft is a new sense organ for the world, one that listens to depth rather than slope, that hears weather and water in the same language it hears mountains, and that can be deployed in basements and on rooftops rather than only from orbit. The closing thought is tender but firm. When you discover that gravitational potential sets the rate of clocks, you realize that timekeeping is not an abstract bookkeeping exercise. It is an environmental science and a geodesy and a test of first principles woven together. A clock does not merely tell you what time it is. It tells you where you are in the universe's energy shape, and by comparing many of them, patiently and honestly, you can watch that shape breathe. In a noisy century that must measure its own change to manage it, there may be nothing more quietly useful or more beautiful than a heartbeat that doubles as a map. Temporal bell tests. You're used to asking whether two distant things are secretly coordinating, but here's a subtler challenge. Can a single system coordinate with its own past in a way that no classical storyline could explain? This is the point of temporal Bell tests, better known as Leggett-Garg tests, and they ask whether a system carries definite properties at all times that could, in principle, be read without disturbing it, or whether quantum mechanics forces you to surrender that comforting picture even when nothing flies across space. The classical stance, called macro-realism, carries three friendly promises. First, that a macroscopic observable has a definite value at every moment. Second, that you could in principle check that value without changing its future. And third, that the future can't rewrite the past. With those promises, there are strict consistency, bounds on how strongly measurements at different times can correlate. Think of them as rules for how often your yes at the first check can line up with yes or no at the later checks. Quantum mechanics predicts that if you prepare a system in a coherent state and sample it at just the right intervals, those time-separated answers can correlate more than any macro-realist story allows, even though you've only watched one object evolve. The catch and the art lie in measurement. Touch too hard and you ruin the very coherence that makes the test interesting. Touch too gently and skeptics can say your apparatus cheated by nudging the system. Experimentalists thread this needle with two families of strategies. One uses weak measurements, so light-fingered that each single shot barely tells you anything. But across many repeats, the average shift reveals the system's mid-course tendencies without clobbering them. The other uses ideal negative result checks, arranging detectors so that a non-click carries information while credibly claiming not to have interacted. If you only count the runs where nothing happened at the probe, you've learned something without a push. Across platforms, superconducting qubits on chips, spins in diamond centers, trapped ions, photons stepping through interferometers, and even nuclear spins in molecules. Teams have reported time correlation patterns that breach the macro-realist bounds when invasiveness is controlled, closing the clumsiness loophole that would otherwise excuse the violation as mere experimental heavy-handedness. What does such a breach mean? It doesn't say the future literally acts on the past, nor that measurement is mystical. It says you can't keep all three promises at once. Either properties aren't definite between checks, or attempted non-invasiveness is a fantasy at quantum scales, or both. That conclusion is striking precisely because no spatial separation is involved. You don't need entangled partners across the lab to see non-classicality. The weirdness lives in the timeline of a single object. Once you accept that, practical uses appear. Temporal violations serve as witnesses of coherence in devices you hope to use as quantum memories. Set up the timing of your checks, and a clean breach tells you the system preserved phase information long enough to outrun any classical mimicry. In sensing, the same idea helps calibrate how strongly your probe perturbs the thing you're measuring. Arrange a sequence that would violate the classical limit if your touch were light, and the size of your shortfall tells you how invasive you were. In communication and randomness generation, temporal correlations can certify unpredictability under weaker assumptions than full device trust. You assert only that measurements happened in sequence on one system, then use a violation to bound how much a classical eavesdropper could have guessed. In quantum control, these tests guide pulse design. The intervals that maximize a temporal breach often coincide with the intervals that maximize information gain per unit of back action, making them sweet spots for readout without ruin. The story has grown richer too. Variants called temporal steering ask whether an earlier action can steer later statistics in ways no classical hidden model can simulate. Entropic forms turn the bounds into statements about the minimum uncertainty you must accept when predicting sequences. And contextuality over time reframes the whole exercise as a test of whether outcome assignments can be glued together consistently across different probing schedules. Each variant attacks a different excuse a classical fan might offer, and together they paint a coherent picture. Time-ordered quantum data refuse to be filed into one grand ledger of pre-existing facts. Still, caution is healthy. Real matter is noisy, and macro-realism was meant to speak about macroscopic objects. Translating a violation on a single spin into a verdict about a compass needle or a cat requires engineering ever larger, well-isolated systems and tightening control of invasiveness. Progress is steady, but hard-won. Meanwhile, the conceptual morals are already usable without grand extrapolations. First, whenever you compare measurements across time, ask what hidden disturbance your first glance injects. The very attempt to be non-invasive is a claim that can and should be tested. Second, recognize that statistics over sequences carry structure that single-time snapshots cannot reveal. If two models agree at each instant but differ in how those instants stitch together, temporal tests will tell them apart. Third, adopt a working humility about properties. In quantum experiments, what you are allowed to call a property often depends on the procedure that read it, and changing the time pattern of procedures changes what stories are even coherent to tell. The closing thought is quiet and practical. Temporal bell tests don't chase paradox. They chase honesty about evolution. They let you ask whether a system's history can be written in pencil first and ink later, or whether any writing is already part of the story you'll read. When you see a clean temporal violation, you've learned that the world you're probing resists being summarized as always had it, could have checked it harmlessly. Instead, it invites you to work with carefully timed questions, gentle enough to hear a whisper, yet disciplined enough to rule out self-deception. That's not just philosophy. It's a recipe for building and trusting quantum technologies whose past and future are stitched together by laws that do not bend for our comfort, but which, when listened to with care, will tell you exactly how to measure without lying to yourself. Recoherence. Can lost time return? You've been told that once coherence leaks away, the movie of a quantum system blurs into noise and the arrow of time locks forward. Yet there's a quieter, more interesting truth. Under the right conditions, what looked lost can be gathered, phased back into step and made to sing again. A phenomenon called recoherence that doesn't cheat time so much as retrace how the scrambling happened and then unwinds it with care. Begin with what decoherence really is. Not a dramatic shattering, but a spreading of delicate phase relations into the system's surroundings, like a whisper diffusing into a crowd. Each microscopic interaction records a sliver of which-way information, and the pattern that once let amplitudes interfere collapses into ordinary probabilities when you ignore or cannot control those records. Recoherence asks a practical question, not a mystical one. Can you make those scattered records align in such a way that the original interference pattern returns? In simple, brilliantly concrete settings, the answer is yes. The classic example is a spin echo. Prepare many little magnetic moments to point the same way. Let random fields make them fan out so their joint signal fades. Then apply a sharp refocusing pulse that flips their relative angles. The fast ones now lag, the laggards now lead, and at a predictable later moment, the crowd realigns and the original signal rises from the apparent decay. No one turned back time. You engineered a mirror in phase space, so the phases that wandered outward came back together. A sister effect lives in light and sound as photon and phonon echoes, where short bursts imprint a medium dephase and then spontaneously reassemble a replica pulse whose timing and strength unveil the hidden structure of the spreading. Even single atoms talking to single modes of a field show elegant revivals. In a trapped cavity or a well-isolated chip, an excited atom sharing energy with a single electromagnetic mode will first undergo neat swaps, then seem to collapse into a wash of outcomes, and later, as the discrete set of participating frequencies resynchronize, the original oscillation revives. Collapse and revival not as magic, but as the beat notes of many slightly different rhythms finding their common downbeat again. In more crowded quantum devices, engineers use dynamical decoupling, carefully timed sequences of control pulses, to cancel systematic drifts and refocus random ones, stitching together many little echoes into long stretches of preserved coherence. This has matured from a clever trick into a standard tool for keeping qubits useful, letting them remember for seconds in solids that would otherwise forget in milliseconds. There is an even bolder maneuver called the Loschmidt echo. Evolve a system forward under a known Hamiltonian, then switch the sign of the relevant interactions and watch the system reassemble toward its starting state. A laboratory echo of the old paradox that nature's microscopic laws look time reversal friendly even while macroscopic life does not. The power and the limit are both baked into that description. If you know the scrambling rules and can reverse or refocus them, you can collect what you spilled. If you do not, or if you have spilled into far too many uncontrolled hands, the thread may be too tangled to recover before noise overwhelms you. That divide leads to a sober map of where lost time can return and where it cannot. In finite, well-isolated systems with few relevant frequencies, exact or near-exact revivals are common. In many body systems that scramble information across a huge web of degrees of freedom, recoherence still exists in principle. Unitary dynamics conserve information, but the practical timescales for a faithful return grow fantastically long, the famed recurrence times that outlive planets, and small imperfections act like sand in the gears. Between those extremes lies the terrain where technology lives. Quantum memories benefit from echo sequences tailored to the dominant noise. Quantum sensors use refocusing to cancel environmental hum while letting a target signal accumulate. Quantum error correction combines redundancy and targeted measurements to restore coherence at the level of encoded, logical information even when the underlying physical pieces have partially decohered, a kind of structured recoherence that repairs the story rather than the paper it's printed on. There are subtler demonstrations whose morals are easily misunderstood but worth holding on to. Quantum eraser experiments show that interference can be restored when the which-way information that killed it is not only hidden from you, but actively erased from the total record before the pattern is read. Nothing travels backward to change an outcome, but by arranging the measurement context so that no trace survives of which path was taken, you reopen the channel through which amplitudes can add and cancel. Disordered many-body systems sometimes localize so strongly that entanglement spreads only slowly, and certain echoes survive longer than you would expect, offering extended windows for partial recoherence that are now being explored as shelters for quantum information. Cold atoms in optical lattices, superconducting circuits, and spins in solid-state hosts have all shown variations on these themes. Dieseling collapse into coherence revivals, pulse trains that swap phase errors for timing you can control, and crafty protocols that turn environmental randomness from a thief into a resource you can average away. Yet honesty requires an equally careful inventory of what recoherence does not do. It does not resurrect energy lost as heat into 1,000 uncontrolled modes. It does not let you violate the second law by unmixing a warm cup of coffee. It does not give you license to delay responsibility by promising to undo any measurement you regret. What it offers, instead, is a disciplined hope that where phase has wandered but not been truly destroyed, design can shepherd it back. This hope becomes a design principle once you translate it from metaphor into knobs. Protect a system so that its environment is effectively finite or slow, and recoherence windows open. Embed control that knows your noise, and you can schedule echoes to land where your readout is sharpest. Choose encodings where the fragile pieces fail in ways your recovery knows how to invert, and logical coherence endures through storms that would wreck bare qubits. Then you can ask more ambitious questions with a clear conscience. Could a network of clocks be synchronized more tightly by echoing away fiber noise? Yes, by implementing two-way phase stabilization that is an echo in all but name. Could a sensor hear a whisper buried under a roar by flipping the phase of the roar at just the right moment? Yes, by differential echoes that cancel common noise. Could a many-qubit register remember long enough to run a useful algorithm despite the entropy dripping in from its wiring and substrate? Yes, if you weave together decoupling with active error correction so that physical recoherence buys time for logical repair, and there is a gentler human lesson folded into the physics that is safe to carry beyond the lab. Recoherence does not deny that forgetting happens. It teaches you to ask what was recorded, where, and whether any of those records can be unmade or refocused. It rewards attention to structure. Which couplings scramble phases quickly and irreversibly, which only nudge them in predictable ways, which can be toggled to make the past reappear just long enough for you to learn from it. It encourages patience. An echo takes planning and a deadline. Too soon, and you have not let the differences build enough to read. Too late, and you have lost the chance to catch them before they melt into true noise. And it cultivates respect for scale. The same laws that allow an elegant revival in a tiny cavity predict that a cat will not unpurr, a cloud will not unmix, a life will not rewind. The closing thought is as soft as it is firm. Lost time does not return in the sense of erasing what happened, but coherence that seemed gone can return as understanding if you trace the path it took into the world and design the mirror that sends it home. In physics, that mirror is a pulse, a reversal, a code. In your work, it is a protocol that separates signal from clutter and gives fragile patterns the chance to stand together again. Either way, recoherence is not a loophole in time. It is a craft of listening, aligning, and for a moment, letting the scattered parts of a story find the shared beat they never truly forgot. Recurrence times in finite worlds. Open a sealed box of moving particles in your mind and ask a question that sounds naive, but is quietly radical. If the world inside is finite, finite energy, finite volume, finite ways to arrange itself, must there come a day when the scene, down to an arbitrarily fine tolerance, returns to something astonishingly close to how it once was? This is the intuition behind recurrence times, a promise that in bounded, isolated dynamics, the movie does not wander forever, but eventually revisits its earlier frames, not by magic or time travel, but because there are only so many distinct rhythms to combine and only so much room to roam. The classical version, descended from Poincaré's theorem, says that a system evolving without friction in a confined region of its state space will, if you wait long enough, come back as near as you like to its starting point. And the quantum version is even cleaner to picture. When a system's energy spectrum is discrete, its evolution is built from a handful of well-defined frequencies whose beats and counterbeats eventually align, producing revivals that reassemble the initial wave with exquisite fidelity. The catch, and the heart of the lesson, is the scale of long enough. In small devices or simple atoms with only a few active frequencies, you can watch exact revivals within laboratory time. In large, many-particle worlds, the number of effective frequencies explodes. Their ratios rarely line up neatly, and the time you must wait balloons to numbers that make the age of the cosmos look like a coffee break. A gas in a liter bottle, left perfectly isolated, has a recurrence time that grows roughly like the exponential of its entropy, since entropy counts in a precise combinatorial sense. How many microhistories fit a single course description like room, temperature, air, the wait for a close rerun scales? Like e to a number with as many digits as there are molecules, which is to say, effectively, never for any practical civilization. That gap between principle and practice is not a loophole. It is the content. Recurrence times teach you why irreversibility and the second law are safe in daily life, without being absolute metaphysical commandments. Dynamics at the microscopic level preserve volumes and, in closed quantum models, preserve the total information. But mixing among an astronomical number of configurations makes the return so remote that the arrow of time, as you live it, is statistically guaranteed. This is also where chaos clarifies rather than confuses. Chaotic motion does not violate recurrence. It strengthens the practical arrow by scattering nearby histories so thoroughly that to land in the tiny neighborhood that counts as the same requires a conspiracy of coordinates beyond imagining. Even though the mathematics still promises that such conspiracies exist if you could wait for aeons that dwarf aeons. A complementary insight comes from the way frequencies stack. When the independent oscillations in a finite system have ratios that are nearly, but not exactly commensurate, the evolution becomes quasi-periodic. It covers new patterns for a long stretch before the phases slip into alignment and a revival appears. The closer those ratios are to irrational relations, the longer you wait. This explains a quiet hierarchy observed across platforms. In a single atom, coupled to one cavity mode, collapses and revivals arrive on human timescales because the menu of frequencies is short. In arrays of cold atoms, revivals appear but degrade as imperfections add more lines to the spectrum. In macroscopic, thermally busy solids, genuine recurrences have times that make counting stars look easy. So we settle for echoes and engineered partial returns that rescue only a sliver of the original order. There is also a conceptual honesty here about what counts as return. The theorems promise a comeback to within any fixed tolerance, not a pixel-perfect rewind. Choose your tolerance too strict and the time diverges. Accept a coarser standard and the schedule shortens. This tolerance is not a cop-out. It is how nature is actually measured. Detectors have finite resolution. Observers summarize reality with coarse variables like temperature and pressure. The same macrostate is a generous basin containing dizzying micro-detail. Within that basin, modest recurrences, like a fluctuation moving a small volume of gas to one corner for a heartbeat, are not impossible. They are just fantastically rare compared with the bland drift toward equilibrium that dominates our experience. The moment you open the box to look, of course, you escort the system out of the realm where recurrence theorems apply, because the assumptions demand isolation and perfectly faithful dynamics. Real environments act like vast, noisy registers that soak up phase relations and smear the exact bookkeeping that a true revival would require. Once countless external degrees of freedom have written their tiny notes about the system's history, recombining them all is a task the world will not volunteer to perform. Yet even that pessimism has a constructive edge. In finite, well-controlled systems with identifiable couplings, ions, superconducting qubits, photons in resonators, we can predict and watch recurrences, or at least partial revivals, and we can decide when to call a pattern close enough to count as the return we want. In many-body physics, recurrence times become a practical yardstick for a device's complexity. The faster observables thermalize and the more stubbornly they resist simple revivals. The richer the web of interactions must be. Conversely, if a model refuses to forget and exhibits frequent clean revivals, it probably hides integrable structure that lets you solve and steer it more easily than a chaotic cousin. In information theory, recurrence is the shadow that gives error correction its purpose. You must build active repair because the passive promise of a spontaneous, faithful return sits on a timescale beyond your lifetime. At the same time, by encoding cleverly, you can make the relevant distance in state space smaller for the variables you care about, so that engineered recurrences, refresh cycles, happen often enough to matter. In cosmology, the idea raises sobering questions we can handle without mysticism. If a truly finite, isolated universe would recur, what sets the boundary conditions that make our arrow of time so strong right now? If our horizon grows and effective degrees of freedom proliferate, do recurrence times blow up, pushing any return forever out of reach? If gravity allows unbounded excursions, does it erase the assumptions that guarantee a comeback at all? Each question refines the same morale. Recurrence is a theorem about ideal finitude. Life is a story about scales and couplings. The soft closing thought is this: knowing that finite worlds carry the seeds of their own return doesn't mean you should expect to meet your past. It means you can locate the source of everyday irreversibility in counting, not in fatalism. You learn to separate what is forbidden from what is merely unspeakably unlikely. You learn to design systems where close enough returns are invited on schedule, and to stop wasting hope on exact rewinds in places where the calendar of the cosmos would run out first. In that clarity, there is comfort. Time's arrow rules your days not because nature refuses to repeat herself, but because she saves her perfect rhymes for a page so far down the book that, for all practical readers, the story moves only forward. Complexity as a time arrow. Watch a simple rule make a tangle. Let many small parts interact for a while. Spins nudging spins, molecules colliding, logic gates flipping qubits, and you'll find that what began crisp and easy to describe turns into a web that's hard to summarize or undo. And that slow drift from simple to intricate can itself serve as a time arrow, a direction you can feel even when traditional thermodynamic signposts have gone quiet. Call it complexity as a clock. The idea that as systems evolve, they typically increase the minimum effort required to recreate or reverse their state. And that effort grows in regular ways you can measure, model, and use. Start with a clean intuition you already trust. Some patterns are short to say, all heads, every other lamp on. Others are long, this exact arrangement of 10,000 lamps. And as interactions shuffle information around, The description you'd need to reconstruct the whole scene tends to lengthen. In computation, this is the notion that a short program often cannot recover a state produced by long, tangled steps except by retracing most of those steps. And in physics, it shows up when a state that started as a neat product of independent parts becomes a richly entangled whole. You can make that intuition precise in several friendly languages. One is algorithmic. If you write the shortest recipe that prints the state exactly, the average recipe length climbs when simple beginnings run under dynamics that mix well. Shuffling cards, running a reversible cellular automaton, letting a spin chain interact, because the data look more and more pattern-free. Another is circuit depth. Pick a simple reference state, restrict yourself to a toolbox of local gates or operations, and ask for the shortest sequence that prepares your current state. As time goes on under generic interactions, that minimal sequence length grows roughly linearly before eventually saturating at a high plateau. And the growth rate depends on how strongly parts talk to each other and how spread out those talks are. A third is operator growth. Rather than track the state, track how a tiny, local poke to the system spreads into a complicated pattern of effects. At first, it touches neighbors, then neighbors of neighbors. The number of pieces you would need to touch to undo the poke expands over time, giving you a contour of increasing undue cost. None of these stories needs heavy symbols to be useful. They are ways to say that the past is usually simpler to summarize than the present, and the present is simpler than the mess you'll have after more mixing. What makes complexity a genuine arrow, rather than a mood, is how universal the growth looks across platforms and how crisply you can relate it to resources. In quantum devices, random circuits built from a small gate set tend to generate states whose preparation depth is close to the theoretical maximum after a time that scales with system size. In many-body lattices, initially local disturbances become global in a characteristic butterfly cone, and the ability to reverse those disturbances with only local tools decays in step with that spread. In models of strongly interacting matter, the scrambling of information proceeds so efficiently that even though the evolution is formally reversible, the cost to reverse mushrooms faster than your control can keep up. Black holes, in the theoretical playbook that unites gravity and quantum information, stand at an extreme. They are conjectured to be the fastest scramblers allowed by nature's rules, and the internal complexity of their quantum state is suspected to grow for a fantastically long time, long after ordinary thermodynamic measures have plateaued. Toy calculations even tie that growth to geometric features like the volume or action of the region hidden behind a horizon, suggesting that in certain regimes the interior grows in lockstep with the difficulty of writing the state from simple ingredients. You don't need to believe the cosmic end of the story to use the near end. In the lab, we already see proxies for complexity growth in the way out-of-time order correlations shrink as operators spread, in the way Krylov measures climb as a simple disturbance explores more basis directions, and in the way random circuits resist compression as you try to compile them into shorter sequences. The arrow that complexity gives you is not the same as the one entropy gives, and that difference matters. Entropy is about how many microstates fit a coarse description, and it tends to rise until macroscopic variables settle. Complexity is about the difficulty of reconstructing the exact microstate by allowed steps, and it can keep climbing long after coarse features saturate, because the details of how the microstate sits in its enormous space can still be growing more intricate, even while temperature, pressure, and other averages are steady. This distinction resolves a common confusion. You can have a system that is effectively at equilibrium, no net flows, thermodynamic arrow at its endpoint, and yet its fine-grained, gate-level description continues to tangle, making the rewind ever more resource-hungry. That is why complexity has become a candidate for a deeper clock in contexts where entropy can no longer tell time. There is also a friendly engineering reading of the idea that helps you judge what's possible. Every attempt to reverse a rich evolution with bounded tools faces two kinds of bills: information, you must know the exact state to astonishing precision, and computation, You must execute a sequence of operations whose length and sensitivity explode as the tangle grows. Even in perfectly reversible models, where no information is destroyed in principle, those bills grow so brutally that the feasible path is forward. Measure, steer, correct on the fly, but do not dream of exact global rewinds. That's not fatalism. It's budgeting. It tells a sensor designer how long you can let a signal mix before the cost of unscrambling it outruns the gain. It tells a quantum computer architect how deep a circuit can be before error correction's overhead becomes dominant. It tells a network engineer when a distributed process needs periodic resynchronization, because the latent complexity debt of the system will soon make recovery too expensive. There is a softer, cross-disciplinary echo of this logic in places that are not quantum. In biology, gene regulation, metabolism, and signaling start as relatively modular motifs in embryos or simple cultures and then interlock as the organism develops or adapts, increasing the number of conditional branches required to describe what happens if. The arrow you feel in maturation or evolution is partly the accumulation of such conditionality. In software, codebases accrue dependencies and implicit contracts, and while good teams refactor to keep complexity in check, the background drift toward harder-to-reverse states is real enough that rollback plans must be built early, or they will be abandoned as too costly later. In economies, the web of credit, supply chains, and expectations thickens over time. Untangling it after a shock is not merely a matter of will, but of computational hardness. None of these examples pretend that complexity is a moral force. They show that the structure of interactions pushes systems towards states where the undo becomes a taller mountain, and that mountain gives direction. With the arrow in hand, you can do more than nod wisely. You can measure and steer. Complexity metrics are imperfect, but improving. Gate counts in restricted toolboxes, compressibility of state descriptions, growth rates of operator support, graph measures of dependency depth. Each metric gives you a speedometer for how fast your system is moving along the complexity axis, and a brake pedal for when to pause and simplify. You can design complexity-aware controls, periodic reset layers in a circuit that project intermediate results into simpler encodings, modular interfaces in software and biology that cap dependency depth, architectural choices in chips and algorithms that keep the cone of influence narrow so local problems remain locally fixable. You can also exploit complexity growth when it helps. Cryptography relies on the expectation that certain evolutions are easy forward and infeasible backward. Secure randomization wants states that resist short descriptions. Privacy-preserving transforms seek mappings that disperse information so broadly that targeted reconstruction has to pay a prohibitive price. The point is not that complexity is always good or always bad. It is that it moves, and its motion is directional enough to tell time. The gentle philosophical payoff is this. When you feel the present as after, you are often sensing not just that more has happened, but that more has to be said to account for what now is. The world accumulates entanglements, logical, causal, informational, and those accumulations are typically one way under realistic resource limits. Seen this way, becoming is not just the addition of events, it is the lengthening of the shortest honest explanation. That's a humbling arrow, because it asks you to replace a fantasy of perfect reversibility with a practice of periodic pruning, checkpointing, and error correction. It is also empowering because it gives you concrete levers and early warning signs. When the cost to explain what you're doing doubles with every small delay, you are not in a neutral drift. You are sliding down complexity's slope, and the right move is to act while the state is still near a simple ridge. So let this be your soft closing. Complexity does not bully you into despair. It invites you to keep a ledger of effort as carefully as you keep one of energy. In places where entropy is silent, that ledger keeps time, reminding you that the future is not just later, but harder to compress. And that wisdom often means choosing paths where the story you'll need to tell tomorrow is still one you can afford to say. Thermal time hypothesis. Open your hand to the warmth of a sunlit window and consider a provocative shift. What if time is not a master clock ticking above the world, but the flow that any physical system derives from its own state of imbalance? a direction encoded in how probabilities are distributed rather than in an external metronome. This is the thermal time hypothesis, a proposal that the pace and arrow of time can be reconstructed from the statistical breadth of the world itself. The gentle entry point is this: every system you can name, gas in a room, electrons in a metal, space-time fields in a region, can be described by a state that assigns chances to its possible configurations. When that state is thermal or close to it, it contains a built-in generator of change, a way of ordering before and after that does not need an outside coordinate. Practically, the recipe says, give me the state, and I'll give you the internal notion of flow that leaves that state looking steady on average, even as it drives expectation values along a path. You then hook your watches and processes to that flow and call its parameter time. This move is radical only if you're used to thinking of time as a background stage. In everyday physics, you already let the state dictate pace, though you rarely say it aloud. Colder systems whisper more slowly. Hotter ones churn faster. Near equilibrium, relaxation sets a tempo for the return to calm. In strongly interacting matter, correlation functions decay on characteristic scales that laboratories read as lifetimes. The hypothesis elevates this pragmatism. Instead of inserting time first and asking the state to evolve, you let the state define a canonical way to evolve and then interpret its parameter as time. Why care? Because the deepest frameworks we use to talk about gravity flirt with the idea that global time may not be fundamental. In formulations where the total energy is constrained and the equations look timeless, you still recover change inside subsystems. The thermal time lens explains how, not by smuggling in a hidden clock, but by noticing that the very pattern of excitations and correlations inside a region singles out a flow. This is not mysticism, it's a disciplined operational stance. Take a physical algebra of observables, the quantities you can, in principle, measure in that region, and a faithful state describing what's there. The pair defines a preferred dynamical rule that leaves the state invariant in a statistical sense. If you build instruments whose readings cohere with that rule, you will find that their schedules align, the way pendulums of differing lengths are reconciled by counting cycles against the same standard note. The science value shows up in places you can touch. In quantum many-body systems, the internal flow recovered from a near-thermal state coincides with the relaxation dynamics that spectroscopists already map. In relativistic settings, local observers who only access a wedge of spacetime find that their restricted view looks thermal and carries its own experienced flow, the origin of familiar phenomena like horizon temperatures for accelerated detectors. In gravitational thermodynamics, the hypothesis offers a unifying language for why the hotter region ticks differently, turning a slogan into a calculation. The state near a horizon encodes a specific ordering that matches the redshifted pace an observer records. In metrology, where clocks are physical devices rather than platonic ideals, the lesson is precise. The better your timekeeper approximates a stable thermal or near-thermal state in a protected subspace, the cleaner the internal flow you can borrow. Drift and bias appear exactly when the device's state is not the one that generates the flow you assumed. Adopting this view also cleans up habitual confusions. It explains why there is no single global now that all regions must share. Different states carve different flows, and only when you have good reason to match them, say, by exchanging light and comparing phases, do you fuse local notions into a networked time. It reframes the arrow. Entropy growth is not an extra principle glued onto time. Rather, the tendency to move from special, information-rich states to typical ones is what gives the internal flow its sense of direction for observers living inside those statistics. And it diffuses false puzzles about reversing time by pointing out that a reversal would mean preparing a very non-generic state whose internal flow runs the other way. That's not forbidden, merely fantastically hard. If you prefer engineering over philosophy, there is a crisp payoff in complex instruments, telescopes stitched across continents, sensor arrays deep underground, quantum processors humming in dilution refrigerators. You can treat synchronization as state alignment rather than only clock alignment, designing subsystems to adopt states whose internal flows agree within controlled tolerances. The result is sturdier coordination because you've matched not just dials, but the statistical engines under the dials. If you prefer reflection, here is a soft but exacting thought to carry. When you ask, "What time is it here?" the thermal time answer is, "Tell me what is here in detail, and I'll tell you which way now leans and how fast it moves." That is not a retreat from objectivity. It is a refinement of it. It says we build time from the inside out. By reading the structure of fluctuations and the balance of excitations in the slice of world we inhabit. And the closing comfort is that this need not make your life slippery. It makes it honest. You will still catch trains and schedule calls because humans have agreed on standards that approximate a shared flow. You will still run experiments against a laboratory clock that is a superb physical instantiation of a stable state's internal tempo. But when those agreements strain, near strong gravity at extreme precision, across mismatched platforms, the thermal time hypothesis hands you a reliable compass. Look to the state, recover its flow and let that be your time. Eidetic echoes in Audition. Close your eyes after a song cuts to silence and notice the faintest remainder, an outline of the last chord that seems to hang in the air even though the speakers have stopped. This is your first glimpse of what we'll call eidetic echoes in Audition, not supernatural recall, but the ear-brain's gift for holding on to sound just long enough to compare, to predict, and to make sense of speech and music as they unfold in time. Under the hood, your hearing carries a short, high-fidelity buffer that neuroscientists often call echoic memory, a rapidly fading store that lingers for a few heartbeats. It is rich enough to keep spectral detail from the just past and flexible enough to update as new input arrives. That store is not one place but a relay. At the periphery, the cochlea acts like a living prism, spreading complex sound into frequency bands along the basilar membrane. Its tiny outer hair cells even push back, amplifying and sharpening the response so that a sudden tone can leave a brief mechanical ring, an after vibration that seeds the earliest persistence. As signals climb through brainstem nuclei, the cochlear nucleus, the superior olive that compares tiny timing differences between ears for direction, the inferior colliculus that begins to blend features, the brain starts building a running sketch of what just happened. By the time activity reaches the thalamus and primary auditory cortex, recurrent loops and short-term synaptic mechanisms give that sketch a thin coat of memory. Not a tape recorder, but a reverberation that lasts long enough to test whether the next syllable, the next drum hit, the next footstep belongs with the earlier ones. You can sense the buffer's power in everyday feats you barely notice. You understand a sentence even if a word arrives a touch late because your system holds the beginning and waits a moment before committing. You follow a melody across a sustained violin note because the overtones your ear just sorted are still present in neural space, ready to be contrasted with the fresh sound. In a crowded cafe, a friend's voice remains, a strand you can keep, pulling because the echoic trace gives the auditory system more than a single instant to decide which bits group together, a process sometimes called auditory scene analysis. The echoes are gentle, but they can be made visible with simple tricks. Play a brief burst of noise that has a notch cut out at one frequency and many. Listeners will report a phantom pure tone in the silence after, the Zwicker tone, an auditory afterimage born from channels that had adapted to the noise band while the notch band stayed fresh. When the stimulus stops, the imbalanced recovery paints a ghost. In another everyday illusion called phonemic restoration, you can bury a piece of a spoken word under a burst of hiss, and the brain will fill the missing phoneme back in, as if it had been there, using the recent acoustic context held in the echoic store plus the expectations of language. No deception is intended. It's how hearing avoids being shredded by interruptions. Even in a normal room, the physical reverberation that bounces off walls blends with your biological echo so that a plucked string seems to glow. Move outside to an open field and the glow shrinks, but the inner echo remains long enough to check pitch and timing against your internal template. What controls the length and clarity of these echoes? Attention extends them a little. Practice refines them. and the statistics of the sound shape them constantly. A steady rhythm sharpens the buffer because the system can predict, reinforcing the right channels. A chaotic soundscape drains it faster because the brain refuses to waste precious working capacity on patterns that will not repeat. Musicians often report unusually vivid inner hearing, a trait that shows up in laboratory tasks as better retention of pitch contours and micro-timing. Yet even non-musicians reveal the same architecture when tested with gentle probes. Electroencephalography, for example, shows a reliable brain signature called mismatch negativity when an unexpected tone violates a recent pattern. That signature is the footprint of an internal comparison. Today's sound against the protected echo of the last few moments. The echo is not flawless. It can mislead. Listening to a constant high tone for a while can make the next mid-range tone sound lower than it is. A contrast effect born from adapted channels. Staring into a loud pink noise track can make a soft tone afterwards seem brighter than it ought. At the extremes, when inner ringing never abates, people suffer tinnitus, a pathology where spontaneous activity or maladaptive gain control is mistaken for a permanent aftersound. There the echo has escaped its proper leash, but most of the time, persistence is a blessing tuned by physiology, the cochlear's elastic mechanics, the thalamocortical reverberation, and the cortical microcircuits that sustain a whisper of activity for a second or two together create a sliding window that is just wide enough to stitch moments into phrases, beats into meter, steps into a pattern that says someone is behind you rather than a random rustle. That window is adjustable. Stress and fatigue can narrow it. That's partly why noisy parties feel more draining at the end of the day. Quiet and focus can widen it. That's why practicing scales slowly transforms notes into lines you can anticipate and track. Technologists exploit and respect these facts. Hearing aids that clamp down noise too aggressively can feel eerie because they fight the brain's expectation that signals decay with a natural grace. Well-designed devices preserve a tiny tail on transients, so the inner echo and the outer world agree. Audio coders that throw away masked details must take care not to erase the bits the echoic buffer uses for comparison, or compressed music will sound clean but lifeless. User interface sounds are crafted with brief, well-chosen decays, so the auditory system can group them across the noise of a busy environment. Language teachers lean on shadowing exercises, listen and immediately speak, to yoke the momentary echo to motor memory, turning a fragile trace into a durable habit. You can experiment with your own buffer in a minute. Stand in the doorway between two rooms and clap once. Notice the physical room echo die while a softer memory ring remains for a blink after. A sense that the clap spectrum is still present even in quiet. Play a pure tone on a phone keyboard or tuning app and stop it abruptly. Listen for the aftercolor in the silence. A faint sense of pitch that is not in the air, but in you. Have a friend read a list of short words aloud at a brisk pace, and insert, every so often, a burst of white noise over one syllable. You will still report most of the words correctly. Not because you lip-read, but because the echoic store and your linguistic priors braided a plausible fill. None of this claims a perfect photographic ear, it claims a humane one. The auditory system balances fidelity with forgiveness. It retains enough of the recent world to test what arrives, and then it lets go. That letting go is as important as the holding on. A buffer that never emptied would prevent you from hearing what's next. If you are tempted to turn this into a moral, let it be a practical one. When you design a learning session, leave small pools of silence after key sounds so the echo can write them deeper. When you mix audio for a crowded feed, keep transients honest and decays proportional so the brain and the room do not argue. When you struggle to catch a voice in wind or traffic, give yourself a few seconds of stillness and the system will recover its templates. And here is the gentle close worth keeping. You do not hear only what is, you hear what just was, braided together by a narrow band of persistence you rarely notice. That band is not a lie. It is the mind's way of giving the world time to make sense. If you listen for it, you will find that silence is never abrupt. It is a soft landing built by a trace that fades with dignity, leaving you ready for the next note. Attention warps, subjective seconds, glance at a waiting room clock during a lull, and a minute feels swollen. Then immerse yourself in a fast game or a dense conversation and 10 minutes vanish. Attention is the hand that quietly stretches and compresses subjective seconds. And once you learn its rules, you can predict, and even design, how long a moment will feel from the inside. Start with the simplest split. When you are prospectively timing, paying attention to time as it passes, your estimates depend on how open your gate to time is. So more attention to the passage itself lets more temporal ticks in and intervals feel longer. When you judge retrospectively, after the fact, you rely on memory richness. So intervals that contained more distinct events or changes are remembered as longer, even if they felt short while happening. This is why boredom drags in the present, but produces thin, short-seeming blocks in hindsight, and why emergencies can feel slow motion in the moment, yet also expand in memory. Arousal pumps detail into the record, while narrowing the immediate beam of attention. Classic laboratory tricks expose the mechanics with pleasing reliability. In the oddball effect, a stream of similar images is interrupted by a novel one, and that oddball is perceived as lasting longer than physically identical neighbors because surprise yanks attention open and floods your internal counter. In filled versus empty intervals, a second bracketed by events and peppered with changes seems longer than a quiet second, because attention hops between stimuli and accumulates more pulses. In dual task setups, asking you to track time while also solving a puzzle or monitoring a display makes the same interval shrink. Attention pulled to the task leaves fewer pulses for the clock. Arousal chemistry modulates the gate. Bursts of noradrenaline and dopamine that accompany novelty, reward prediction, or threat tend to speed the internal metronome. Stimulants make intervals feel longer prospectively, whereas fatigue, low arousal, or certain sedatives slow the count and compress felt duration. These levers are not abstract. People with attention disorders often show characteristic biases in timing tasks, over or underestimating durations depending on whether the demand is to watch time pass or to remember how full the interval was. Parkinson's disease, which alters dopamine pathways, nudges temporal judgments. Anxiety can overexpand brief exposures, especially when the timed stimulus is threatening, by both heightening arousal and steering attention inward. Sensory rhythm can hijack the gate too. Present a flickering light or a rapid click train, and perceived intervals enlarge in step with the modulation rate, as if the brain mistakenly counted the external pulses as internal ones. Increase visual contrast or sound salience, and you lengthen apparent duration by capturing attention more tightly. Lower salience or add predictable monotony and time thins. Multisensory scenes complicate and empower the effect. Sights that lag sounds by a hair can be pulled into subjective sync when attention anchors to the more trusted channel, yet that same anchoring can distort duration whenever one stream carries richer change. In speech, this helps you cope with variable rates and accents. Attention locks to syllabic rhythm, stretching or compressing perceived gaps to maintain intelligibility. In music, tempo and phrasing manipulate your gait deliberately, with composers using dynamic swells and syncopation to make passages feel breathless or suspended without changing the clock. Technology lives on these truths. A loading spinner that changes in small, frequent, informative ways feels shorter than a static bar for the same weight, because attention is fed and the retrospective judgment grows. Interface sounds with crisp onsets and natural decays give your echoic memory anchors, reducing the anxiety that expands a silent wait. Tutorial flows that partition a task into bite-sized, varied steps shrink perceived onboarding time compared to a single long screen. Even sports lean on the science. Coaches constrain drills to tight, salient cues, whistle bursts, colored lights, short rhythms, so that athletes' attention pulses align with action windows, improving time-to-contact judgments that would otherwise wobble under stress. Broadcasters cut replay sequences at attention-friendly rhythms to make the same 15 seconds feel satisfyingly dense. You can test the levers at home. Try a 1-minute prospective estimate with eyes closed and nothing to do. You'll likely overshoot because your gate sits open, counting bodily pulses and faint environmental rhythms. Try again while playing a fast-paced puzzle, and you'll underestimate as attention is taxed. Then repeat with a metronome or breath counting. Suddenly, the minute feels fuller and longer because you've added structure for attention to latch onto. Now reverse the lens and judge retrospectively. Spend 2 minutes in silence staring at a blank wall versus 2 minutes skimming varied images. The latter will feel longer in memory because your brain stored more distinct tokens to reconstruct the interval. These are not parlor tricks. They settle everyday debates. The complaint that meeting took forever can be dismantled into attention starvation. No novelty, few state changes, coupled with a high prospective focus on time, watching the clock. Whereas the commute flew by mixes divided attention, podcast plus driving, with a retrospective thinness, few landmarks remembered. The same analysis suggests remedies kinder than cynicism. Add meaningful micro-events, checkpoints, small decisions, feedback chimes, to long tasks to reduce the drag. Build attention anchors into anxious waits, progress snippets, brief movement prompts, to keep the gate busy. Alternate focus sprints with short, varied breaks so both prospective and retrospective systems remain balanced. On the contemplative side, practices that train attention, mindful breathing, body scan, slow listening, reliably expand the felt present by stabilizing the gait and reducing jitter, making short spans feel more spacious without distortion. But they also make retrospective time more nuanced, because memory receives a richer, more continuous record. Conversely, doom scrolling compresses the now, constant novelty taxes attention, while bloating the afterward, too many micro moments to reconcile, leaving you disoriented about where the evening went. The science also cautions against overreading personal narratives into elastic seconds. People in accidents often report time slowed down, yet careful experiments suggest that what changes is not the sampling rate in the moment, but the density of memory laid down under high arousal. The emergency feels slow because the replay is rich. Understanding that spares you the myth that danger grants superhuman temporal vision, while preserving the truth that attention and arousal reshape experience profoundly. The gentle closing is practical and humane. Subjective seconds are not lies. They are customized clocks your brain builds to keep you effective. When attention is underfed or overdriven, the clock misscales your life. When attention is well-shaped by rhythm, meaning, feedback, and rest, time becomes kinder and more accurate for the tasks at hand. Design your days with that in mind. Choose when to open the gate and count, when to let memory richness do the work, and when to give both a pause. In that choreography, you'll find not only better performance, but a steadier sense that your hours, however measured, belong to you. Multistable perception and time. Hold your gaze on a Necker cube or a Rubin vase and feel a quiet tug of war. The picture doesn't change, yet your seeing does, flipping between interpretations like a coin that refuses to land. Multistable perception is a living lesson that time in the mind is not just what a clock says, but what a system does while settling, lingering, and switching between rival stories. At first, the alternations feel random, but patterns sit under the surface. Each dominance phase, when one interpretation is vivid and the other suppressed, lasts a few heartbeats on average, and the probability of a switch rises with time the longer a view holds, like pressure building toward release. The exact rhythm depends on stimulus strength, attention, and internal state, which means you carry a personal tempo for ambiguity. The engine behind this dance mixes adaptation and competition. Neurons or populations supporting one interpretation tire as they fire, while their opponents recover. So a favored story gradually loses grip. Noise in the system, tiny fluctuations in incoming signals, and ongoing brain activity then nudges the weakened winner over the edge, letting the rival take the stage. Crucially, this is not mere eye trickery. Binocular rivalry, where each eye receives a different image, proves the flip can occur even when the inputs are constant and segregated. Structure from motion displays, where moving dots suggest a spinning object that reverses direction in your mind, show that the switch lives in how the brain resolves causes, not in the dots themselves. Even tactile and olfactory variants exist, reminding you that multi-stability is a computation principle, not a quirk of vision. Time enters twice. in the shape of dominance durations, neither perfectly regular nor wildly chaotic, often clustered around a typical span with a tail of longer holds, and in how external pacing and internal rhythms modulate those spans. Add a subtle periodic cue, an audio click, a brief dimming, a fingertip tap, and your switches may synchronize loosely to that beat, as if external metronomes can coax the system's hazard to rise on schedule. Remove all cues and the alternations still march on, driven by the system's own fatigue recovery cycles. Attention bends the tempo without dictating the outcome. Aiming your focus can lengthen the current percept's reign, but only to a point, because adaptation keeps eroding your grip. Divide attention with a secondary task, and the mean duration can shrink as if neglect hastens the handover. Arousal and neuromodulators play conductor. Heightened alertness, caffeine, or mild stress often quicken the pace, while drowsiness stretches plateaus. Clinical states leave distinct fingerprints. Certain medications slow switching. Some psychiatric and neurological conditions shift the distribution of dominance times, and these signatures are now studied as potential behavioral biomarkers of underlying circuit imbalances. The geography of the brain's involvement has been mapped not by speculation, but by converging evidence. Early visual areas preserve competing interpretations in parallel. Motion-sensitive regions like MTV5 lean one way, and then the other in structure from motion. Parietal hubs help arbitrate which interpretation wins access to awareness, and prefrontal networks appear to monitor and bias without directly drawing the picture. When researchers apply short pulses of magnetic stimulation to these regions at chosen moments, they can tilt the odds of an imminent flip, showing that the system is perched near a threshold long before the subjective switch happens. When they record with EEG or MEG, they find slow drifts in attention networks and transient signatures that predict an upcoming change a fraction of a second in advance, the brain's quiet prelude to a new interpretation. Multistability also exposes a deeper rule about experience that's easy to miss. The mind treats time as an opportunity to test a hypothesis until evidence or fatigue demands another try. In ambiguous scenes, that test repeats: hold, evaluate, tire, switch. In speech, when an ambiguous word arrives, your language system briefly entertains alternatives until context decides. In social perception, a face with a mixed expression can tilt from friendly to skeptical as you gather more cues. In scientific reasoning, a data plot may look like one pattern until additional points make a rival fit irresistible. The same attractor logic gives these domains their characteristic feel of being stuck and then seeing it differently, and the intervals between flips, though less obvious than in a drawing, still shape how you live time while deciding. Practical consequences flow once you see the machinery. Interface designers can reduce fatigue by avoiding sustained ambiguities that force constant flipping. A logo that can be read two ways delights at first, but will tire if it anchors a workflow. Educators can stage demonstrations that let students feel the cost of holding a hypothesis, then deliberately trigger a switch with a small new cue, teaching that conviction absorbs energy and that interpretation is dynamic rather than binary. Therapists who work with anxiety can use multistable images as a safe training ground. Clients learn that uncomfortable uncertainty has a rhythm, and that switches, though unpredictable, are lawful and survivable. They practice attention strategies that lengthen calm phases without trying to control the uncontrollable. Musicians and sound engineers can exploit auditory multistability, where streams of tones group and regroup into separate lines or a single melody. By shaping tempo and timbre, they choreograph when the listener's perception will fuse or split, turning time into a compositional parameter rather than a fixed grid. Scientists, finally, use dominance durations as windows on brain health, because switching reflects a balance of inhibition, adaptation, and noise. Changes in that balance due to development, aging, or disease show up as measurable shifts in the statistics of perceptual time. You can explore your own dynamics in a few minutes. Print a Necker cube, stare softly, and count in your head how long each percept holds. Now add a steady breath rhythm and see whether your flips align with exhales. Next, play a faint metronome and notice whether a switch prefers to land on certain beats. Try binocular rivalry on a phone app and learn how gentle blinks or micro-eye movements can reset fatigue and trigger a change. Breathe faster and watch the tempo quicken. Practice a focus drill. Narrow attention to a single edge and feel the reign of a percept lengthen before adaptation erodes control. These tiny experiments teach 3 transferable lessons. First, holding a view is metabolically and computationally costly. Fatigue is not failure, but a signal the system uses to avoid locking on one story when evidence doesn't force a commitment. Second, switching is not caprice but a safety valve. It protects exploration by preventing local certainty from becoming a trap when the world is underdetermined. Third, timing is a tool you can design with. By providing oases of unambiguous cues at the right intervals, you reduce needless alternations. By introducing controlled informative ambiguity, you keep perception flexible and alert. The philosophical echo is gentle but firm. Reality may be single, but access to it is staged. And part of what you experience as the flow of time is the brain's rotation through viable narratives when the data are thin. Multistable perception does not prove that truth is relative. It proves that arrival at truth is dynamic. A process with dwell times, thresholds, and renewals that give subjective minutes their texture. Accepting that does not weaken your grip on the world. It strengthens it, because you stop mistaking fatigue for doubt. You learn to schedule clarity where it matters, and you grant yourself patience where ambiguity is inescapable. So here is the soft close. The cube will keep flipping, the vase will keep becoming faces, and the mind will keep time with those alternations, not to tease you, but to keep you awake to possibilities until the right cue locks one in. If you listen to that rhythm rather than fight it, you gain a steadier way to see. Let a view be vivid. Let it fade, let another rise, and with each cycle, let your sense of time become not a prison of seconds, but a practice of noticing when to hold and when to turn the page. Decision latency versus awareness. Notice the tiny hesitation between seeing a yellow light and choosing whether to brake or accelerate. That sliver is where decision latency lives, and it is not the same as the moment you become aware of having chosen, which often arrives later and with a tidy story attached. Understanding the gap, how long it takes a brain to settle on an action, versus when the mind claims ownership of that settling, gives you practical leverage over errors, overconfidence, and the false certainty that I decided right then. In simple terms, a choice is usually an accumulation of evidence toward a threshold, noisy samples, glimpses of motion in the periphery, a tone that might be higher, a hint that an email is urgent, are integrated until a bound is hit, which triggers a commitment. The latency you measure with a stopwatch mostly reflects how fast evidence piles up, plus a few fixed lags from sensing and muscle execution. Awareness, by contrast, rides on access. Once a commitment is underway, signals that summarize the state of that internal race are broadcast to systems that can report, narrate, and remember. Those access signals are not instantaneous and they can be fooled. You can feel the difference in well-studied tasks without learning any jargon. Ask people to pick which of 2 dotted patches moves coherently to the right. When the dots are very clear, decisions come fast and awareness of deciding feels nearly simultaneous. Lower the coherence and reaction times stretch, while subjective timing gets slippery. People often report deciding a hair earlier than the actual muscular commitment if they were confident, or later if they were wavering. In speed-accuracy trade-off games, when you urge speed, the bound is set low and actions fire quickly, but with more regret. When you urge accuracy, the bound rises, latency grows, and awareness feels more deliberate, even if the underlying sensory sample was the same. Crucially, your awareness meter can lag or lead your action. In change-of-mind experiments, people sometimes start to move toward one option, and a few tens of milliseconds later, curve the hand to the other as new evidence tips the balance. Yet many will say they knew all along, or they decided at the last moment, depending on which narrative makes the motor outcome feel coherent. Physiologists see matching traces in the brain and body. Slow ramping activity in decision hubs builds toward a bound. A separate, more punctate signature reflects the moment you deem something worthy of report. and micro-twitches in muscles reveal partial, aborted commitments that never make it to the eye, but still color the story you tell yourself. Confidence threads these pieces together. When the integrated evidence at commitment is far beyond the bound, you feel sure and awareness of deciding seems early. When it only barely crosses, confidence is shaky, and the felt decision time shifts later, as if your mind waited for a reassuring echo before claiming ownership. Urgency controls add another twist. In tasks with deadlines, an internal timer effectively pushes activity upward, so the bound will be hit on time even if the evidence is weak. The action is earlier, the error rate rises, and awareness often rationalizes after the fact, "I had to go for it," which is functional on a racetrack, but dangerous in triage. You can even separate decision latency from report latency. In some paradigms, participants make a categorical choice with one hand and, with the other, continuously report how sure they are. The categorical movement can precede the peak of confidence by hundreds of milliseconds, showing that commitment and the awareness of being committed are distinct processes that only sometimes align. The lesson is not that awareness lies. It is that awareness is a summary produced on a schedule and with priorities, coherence over micro-timing, utility over perfect audit. This distinction offers concrete tools. In interface design, surface early pre-decision cues, subtle highlights that make relevant evidence easier to accumulate, so latency drops without forcing users into low-bound rushing. Then request explicit confirmation when confidence is likely to be low, because awareness will otherwise backfill a shaky choice with a confident-sounding narrative. In safety-critical domains, separate the go from the why. A pilot can commit to a go-around quickly, while a second display aggregates confidence over a longer window to justify or question the move, preventing a snap action from locking in a snap story. In sports, training that feeds graded, informative noise around the target helps athletes tune their bounds so that latency adapts without letting awareness lag dangerously. Debriefs reference partial error metrics, micro-EMG slips, mouse trajectory bends, so players learn to notice early tells that an automatic commitment has launched without adequate evidence. In medicine and hiring, insist on a two-stage cadence. Fast provisional classification followed by a timed, structured reflection, so that the system benefits from the speed of accumulation, but grants awareness a second pass with fresh evidence to catch late-arriving reasons. Even everyday decisions improve when you respect the gap. If you must act fast, replying in a tense thread, making a lane change, set bounds in advance. If 3 cues line up, I move. Otherwise, I hold. Shrinking latency without surrendering control. If you can act slow, collect more samples and expect your felt moment of deciding to creep as confidence stabilizes. There's also a kindness to carry. In disagreements, assume the other person's choice crystallized before their awareness of why did, because that's how your mind works too. Ask for the evidence they had at the moment, not only for the story they can tell now. For students and teams, teach the signs of premature commitment, impulse starts, confirmation seeking attention, versus paralysis, ever-rising bound, zero accumulation. Then give tactics to nudge each back toward the productive middle. Time boxing to force a decision when evidence will not improve. Checklisting to slow a reflex when stakes are high. Finally, use your own physiology as feedback. If you feel a motor plan in your hands or posture before your reasons are in focus, that is your accumulation engine announcing a near-threshold state. Breathe. Widen the sampling window by seconds and let awareness catch up so the narrative you adopt matches the action you are about to own. The gentle close is simple. Decisions are not flashes, they are rises. And awareness is not a spotlight that triggers them, but a lamp that illuminates them once bright enough to share. When you separate the two, you stop mistaking speed for certainty. You design environments that let evidence speak in time, and you grant yourself the small patience that turns quick choices into choices you can defend. Neural predictive timing. Picture your brain not as a metronome that counts what already happened, but as a quiet choreographer that constantly forecasts when the next moment should arrive, so it can meet it half a step early. This is neural predictive. Timing The skill that lets you catch a ball that isn't yet in your hand, finish a friend's sentence on the breath before they do, and hear a skipped beat as a mistake rather than as silence. To understand it, you have to accept that the nervous system does not simply register time, it expects it, shaping perception and action around anticipated arrivals. The forecasting shows up across several cooperating clocks. One is rhythmic entrainment. When sound carries a beat, activity in auditory regions and motor circuits locks onto the rhythm, with slow neural oscillations lining up their high excitability. Phases to the expected onsets so that incoming notes land on receptive tissue. Disrupt the beat and you feel it instantly because your cortex was leaning forward, prepared for an arrival that didn't come. Another is interval timing. When a one-off event is likely after a fixed delay, the start of a race, the blink between two lights, networks in frontal cortex, parietal cortex, and the cerebellum build a hazard expectation that grows with elapsed time, a gently rising readiness that peaks when the world should act. The moment the cue appears near its expected time, reaction speed improves and sensory thresholds dip, as if perception were being primed not only for what, but for when. The cerebellum brings millisecond precision to this, calibrating short anticipations through its dense loops so that eye and hand movements arrive on schedule, while basal ganglia circuits help with beat-based timing over longer spans, a division of labor musicians exploit without naming it. The snap of a pick attack owes to cerebellar tightness, the feel of the groove to striatal scheduling. Still other systems forecast on their own timescales. Speech areas align to syllabic rhythms in the delta and theta range, letting comprehension ride the crest of expected syllable onsets. Motor regions subtly bias auditory processing so that predicted syllables arrive in phase, which is why reading a line aloud can clarify a muddled accent. Your motor plan supplies a temporal scaffold that the ear follows. The hippocampus, famous for mapping space, also maps unfolding episodes. As you approach a learned event, certain neurons advance their firing earlier in a cycle, a phase precession that can be read as how soon rather than how far, letting memory cue the now with a forecast of the next beat in a sequence. And dopamine, the brain's teaching chemical, does more than grade what predictions. It also grades when. When an expected outcome arrives early or late, brief dopamine pulses shift in time, training circuits to tighten or relax their temporal expectations until prediction error shrinks. This is why you feel a tiny jolt when a traffic light changes a fraction later than usual. The error signal is real. Evidence for the brain's devotion to when is everywhere once you look. In laboratories, a faint flash presented at a predicted time is seen more often than the same flash at an improbable time, even though the energy is identical. In music studies, listeners identify mistimed notes faster than mistuned ones when a strong beat is present because temporal violation screams against a well-formed expectation. In sports, batters and goalkeepers are trained on variable interval drills because over-regular timing makes their predictive models brittle. When experimenters jitter the time of a critical cue, preparatory neural activity that had been rising like a ramp spreads out and weakens, and the benefit of expectation fades. Add a light metronome under noisy conditions, and perception recovers because attention can now ride a reliable scaffold. The predictive timing system is also smart about uncertainty. When the environment is regular, it narrows its temporal window, becoming picky and fast. When the environment is erratic, it widens the window, sacrificing sharpness for tolerance, a Bayesian wisdom that keeps you from overreacting to noise. Self-generated timing is another revealing arena. Before you speak, play a note, or tap a key, motor systems send a copy of the plan to sensory cortex that says, in effect, sound incoming at this moment, and the auditory system dampens its response exactly on time, so your own voice does not startle you, a cancellation that fails if the timing is off. which is why delayed feedback of your speech feels alien. The brain expected a self-caused sound now, not later, and flags the mismatch. In movement, predictive timing keeps your world stable. Just before a voluntary movement, certain visual neurons transiently downweight sensitivity so that the reafferent flood from your own motion does not swamp the scene. If the downweighting is time-shifted by even a fraction, the world seems to smear. The reach of these mechanisms explains both everyday grace and specific vulnerabilities. People with Parkinson's disease often struggle when a task relies on internally generated beats, but improve when the world provides a strong external rhythm, visual stripes on the floor, a metronome through headphones, because the predictive schedule they can't build internally arrives from outside. Children with developmental language disorders benefit from rhythm-based training that sharpens their temporal scaffolds for syllable parsing. Some forms of dyslexia involve shallow temporal sampling that blurs consonant timing, and exercises that emphasize beat alignment improve phoneme discrimination. Even clinical anxiety bends felt time through prediction. When the hazard model is set too high, the brain expects danger too soon, making neutral intervals feel overlong while keeping the system in a premature state of readiness that exhausts it. You can work with these truths rather than be worked by them. If you need to improve perception in noise, introduce a mild, relevant rhythm, breathing cues in meditation, soft clicks in a lab protocol, a pulsing haptic in a cockpit. So, attention. Can lock and sensory gain can peak at the right moments. If you need to avoid being fooled by your own predictions, randomize the timing of practice trials so your model stays flexible instead of brittle. In classrooms, present new material in temporally structured bouts, short, reliable cycles of example and test, so that students' internal hazard models anticipate when to engage. In user interface design, replace static weights with micro-progress that updates on a cadence aligned to human sampling rates, reducing the anxiety that blossoms when the brain's expectation of when receives no feedback. In teamwork, time your requests and handoffs against established rhythms, daily stand-ups, fixed review slots, not to be bureaucratic, but to give predictive timing a stable lattice so that cognitive effort peaks when it pays. At a personal level, you can tune your own clocks. Practice a simple sensory-motor sync each day. Tap lightly to a metronome, then switch to tapping to delayed echoes, then back, so your cerebellum and basal ganglia keep both short-interval and beat-based predictions fresh. Rehearse speeches with an awareness of phrasing, as if you were conducting, so your listeners' auditory systems know when to expect emphasis. Vary the timing of rewards to yourself, breaks, treats, to keep dopamine honest, avoiding the dullness that follows. Perfectly predictable schedules. Finally, let the philosophy land softly. Predictive timing does not claim that you invent time. It claims you carry a model of time's local texture that is revised by experience, and that this model quietly organizes what you see, hear, and do. The payoff for respecting that model is practical and humane. You forgive yourself for missing a cue if the world broke its own pattern. You design days with pulses that keep attention ready at the right instance. You train flexibility by occasionally stepping off the beat so your forecasts do not become prisons. In a world that rarely announces its schedule, becoming skilled at forecasting when is the difference between feeling sprayed by moments and feeling like you can meet them with grace, often a breath before they arrive. Causality breakdown. Thought experiments. Imagine you could pass a folded note to your earlier self and ask whether the universe would tolerate the delivery. Causality breakdown. Thought experiments begin there, not to license time travel fantasies, but to stress test the guardrails that keep before and after from tangling. And by walking right up to the edge, you learn why the rules are what they are, where they bend, and how to reason clearly when intuition falters. Start with the friendliest trap, the bootstrap loop, in which an object or idea seems to exist without origin. a violin concerto copied from a score you found in your attic, which turns out to be the one you yourself placed there after traveling back. So who wrote it? Or a tool you mail to your past self that enables the very time machine used to mail it? This isn't mere whimsy. It forces you to ask whether physics insists on a unique history, or merely on a history that is locally consistent. One proposed antidote, the self-consistency principle, says closed loops are allowed only if all events along them fit together without contradiction. You can leave the concerto in the attic if, and only if, no microscopic law is broken by its looping existence. Another, from quantum information, treats loops with post-selection logic. Among all possible outcomes, only those that do not generate paradox survive. A rule that keeps stories tidy but demands improbably precise alignments. Push further and you run into the grandfather paradox, where you try to prevent your own existence. Versions that obey self-consistency simply route you toward near misses, jammed doors, misfires, sudden distractions, until the loop closes without killing the storyteller, not by magic but by the requirement that, if you're there to attempt the act, you must also have failed. Notice what these exercises teach without equations. They do not prove time travel is real. They prove that if you imagine it, you must also imagine constraints that make timelines coherent. And those constraints are so tight that any would-be history breaker is squeezed back into compatibility. Replace travel with faster-than-light signals and a new trap springs. In relativity, different observers slice space-time into past, present, future differently. If you allow a message to outrun light, someone somewhere can turn it, with a clever sequence of frame changes, into a message arriving before it was sent, enabling reply before ask loops that threaten logic. Thought experiments here are brisk. A pair of transmitters exchange superluminal pings, and thanks to relativity of simultaneity, each receives the other's ping first, opening a channel to contradiction. The moral is crisp. The speed limit protects more than technology. It protects order. This is why entanglement, despite its uncanny correlations, is framed carefully. Quantum theory gives you strong statistical patterns between distant systems, but denies you any usable signal faster than light. If a scheme seems to promise otherwise, a sober bookkeeping of who knows what, when, reveals that the apparent message dissolves when data are pooled. Stretch your imagination again, and consider closed time-like curves, world lines that loop in space-time so that a traveler's future meets their own past. Classical versions demand consistency. Quantum versions invite multiple proposals. In one, evolutions through the curve are constrained by fixed-point conditions, so that the state you send in is the state you must receive out under the looped dynamics. Thought experiments show you can solve certain otherwise hard computational problems by exploiting this constraint, but at the price of a world that has already pre-filtered contradictions. In another, histories branch and recombine, so that the traveler entering the curve emerges into a distinct but related record, a stance that deflates paradox by allowing many tapes rather than one. Yet it forces you to accept that what happened is indexed by a path through a landscape of possibilities rather than by a single ledger. Each model saves causality in its own way. Each demands clarity about what counts as a cause when loops exist. Shift scale and play with delayed choice scenarios. Arrange an experiment so that you decide later whether to reveal a particle's path or its wave-like interference, tempting you to say the later choice reached back and rewrote the earlier event. The clean resolution is conceptual. Your later setting changes the type of question you ask of joint data, not the earlier facts. Until you pool information from the separate records, nothing paradoxical occurs. And when you do pool them, the pattern follows the rule that you chose, no faster than light whisper needed. These vignettes are not toys. They are filters that separate sloppy talk from workable principles. For instance, they motivate causal order as a resource. Even if certain quantum protocols can place the order of operations in superposition inside a well-shielded device, those protocols still bow to ordinary causality at the point where results are read. Any attempt to smuggle a contradiction out into the macroscopic world hits the same wall. A record cannot both exist and not exist at one and the same time and place for the same observer. The exercises also sharpen your sense of information as the currency of cause. A cause is not just an earlier event. It is earlier, and it can, in principle, be used by an agent to change the odds of a later outcome. Many illusions of breakdown vanish when you track who could have known what when without already assuming the very information they purport to transmit. Paradoxes tend to sneak in a hidden side channel or a forgotten conditioning step. Still, not every challenge evaporates. The best thought experiments leave genuine friction that turns into research questions. Could gravity at the quantum scale permit situations where temporal order is fuzzy without enabling contradictions? And if so, what inequalities constrain such fuzziness? Are there consistency-preserving rules that allow loops to compute or communicate in ways that classical circuits cannot? And what do those rules imply about complexity and cryptography? Can we define experiments that would fail if the world were secretly a causal, thereby using success as evidence that causal structure is intact at the scales we can touch? On the human side, these puzzles act as mirrors. They reveal how much of your sense of understanding rests on stories where influence flows one way, and where records accumulate rather than dissolve. When a scenario threatens that, your mind reaches for either a hidden constraint, something must block the contradiction, or a larger arena. Many tapes, not one. Neither response is cowardly. Both are attempts to protect the minimal virtues of explanation: consistency, testability, and the ability to condition expectations on available information. This is why engineers who build protocols for networks, markets, and safety-critical systems practice a modest version of causality stress testing every day. They search for signaling paths that could be exploited to create loops, race conditions in code, incentives that let future states influence present choices in perverse ways, and they add constraints or buffers that restore a cyclic flow. In that way, thought experiments about breakdown guide practical design. You insert no feedback zones for decisions that must be based only on past data. You require commit-reveal schemes so that choices cannot be adapted after seeing others. You timestamp, audit, and distribute records to prevent retroactive edits from masquerading as prior causes. The soft closing is this: causality is not a brittle doctrine waiting to be shattered by a clever paradox. It is a fabric woven from locality, signal constraints, consistency, and honest bookkeeping of information. Thought experiments that try to tear it do us a kindness. They show where the weave needs extra threads, where language needs tightening, and where our hunger for dramatic loopholes should yield to the quieter power of principled limits. When you carry that kindness forward, you stop chasing contradictions as trophies and start using them as tools. You imagine the impossible to map the boundary of the possible, and you leave with a clearer sense of why the road bends where it does, and why the world, so far, refuses to let messages arrive before they are sent. The last tick paradox. Imagine a universe that ends on Tuesday at noon. Would there be a final audible tick that closes the ledger of time? Or does the very idea of a last tick dissolve when you look closely? The last tick paradox lives in that tension between our appetite for tidy endings and the way clocks, continua, and physics actually behave when they near a boundary. Start from what a tick is in the real world, not a metaphysical atom of time, but a completed cycle in a physical device. A pendulum swing, a quartz oscillation, an atom's phase advance, registered by a detector that counts and stores state. The paradox arises when we ask this innocent question: if there is a last cycle, how would the device ever know it is last without stepping outside itself to check? And if there isn't, how can a world finish without finishing a cycle? In continuous time, the mathematics already warns you that last instants are subtler than they sound. An open interval can end at a boundary that is never reached from within. Think of approaching noon by reading 11:59, 59:9, then 99, then 9:99. There is no final pre-noon reading, only a limit. If time ended at such a boundary, there would be no final pre-end second to stamp. The movie runs out of frames not because the last frame shows the end, but because the projector stops. In discrete time, by contrast, you might fantasize a final cell on a cosmic spreadsheet labeled teen. Yet even if nature granted such granularity, no finite device can carry a flag that says, this tick is the terminal one, without presuming knowledge of the global schedule, which is precisely what local physics does not provide. The puzzle becomes sharper in famous supertask stories like Thomson's lamp. Flip a lamp at t when 1, 2, 3, 4, 7, 8, so that infinitely many flips occur before t1, then ask whether the lamp is on at t1. The setup seduces because arithmetic welcomes convergent series, but physical clocks don't. Each flip must be triggered, recorded, and dissipated. Every trigger consumes energy and bandwidth. Attempting to halve latencies without bound runs into noise floors, quantum backaction, and finite propagation speeds. In reality, the number of flips you can accomplish in 1 second is not as many as arithmetic allows, but as many as energy, information capacity, and stability let you do. And that number is finite, so the lamp stops being a paradox about time and becomes a lesson in models. Allow infinite idealizations and you get undefined terminal states. Enforce physical budgets and the riddle collapses. Cosmology adds a second kind of last tick anxiety. Could the universe have an ending in finite proper time for observers? And if so, do their clocks tick one final time? In some endgame scenarios, say a big rip where expansion destroys structures in a finite interval, or a world line that terminates on a singularity inside a black hole, an observer's wristwatch indeed accumulates only a finite number of cycles before it is torn apart. But this does not produce an observable last tick as a labeled event. The device does not signal, I have now reached my final count, because such a signal would require a further tick to encode and send it. From within the experience, the clock simply fails during an ordinary tick. Whether that tick happened to be the last is a statement made only by a historian who exists outside the story, and physics gives us no such balcony. In other endgames, time does not end in a slam, but in a fade. As free energy wanes and gradients flatten, processes that sustain ticking become rarer and slower. Oscillators lose coherence, reaction chains stall, and there is no singular terminal tick, only an asymptote towards silence. Here the paradox reverses. No last tick is not a loophole, but the expected texture of dying dynamics in an open-ended continuum. At this point, someone often invokes a hard flaw. Surely the Planck time is a minimal tick. The honest answer is quieter. Planck scales are natural units built from constants. They mark where our current theories strain, not a proven discreteness. Even if a future theory discretizes time, nothing about discreteness guarantees a globally shared counter or a universe-wide final cell. Discreteness would cap resolution, not grant omniscience to clocks. Conversely, quantum limits do place operational bounds on ticking. To resolve ever shorter intervals, a clock must mobilize higher energies or larger resources. Past a point, adding energy creates gravity strong enough to deform the stage you're trying to time, and using too many parts makes the clock indistinguishable from the world it measures. Those bounds don't answer metaphysics. They block the engineering that would turn metaphysics into an experiment. The paradox also feeds on a conflation between personal time and global time. Relativity teaches that there is no single master time. Each world line carries its own proper time, and clocks synchronize only by exchanging signals and agreeing on conventions. Asking for the universe's last tick assumes a universal dial. What we have are many dials that can stop for local reasons at different readings. A star collapsing past its event horizon may finish a finite number of atomic cycles before hitting the singularity. A distant astronomer's clock will keep counting long afterward. Neither supplies a privileged end to the other. Even more, the idea of last presumes a meta-time against which ending is measured, an extra layer our theories don't contain. What then are we actually asked to understand? First, that a tick is a physical act of completion plus a record. Lastness, by contrast, is a global property of a history that cannot be certified from inside. Second, that paradoxes born of infinity at a point, supertasks, are artifacts of ignoring finite capacities. Replace the caricature lamp with a device subject to energy and information constraints, and the infinite cascade dries up before any mystery. Third, that different endings feel different. Abrupt terminations along a world line don't produce labeled finals. Asymptotic die-offs produce no final either, and in neither case is there a contradiction with a world that ends or a process that ceases. From these lessons, you can harvest useful concrete habits. In computation, avoid designs that rely on detecting a last iteration by local signs when the stopping condition hinges on external horizons. Use watchdogs and budgets rather than mythical terminal flags. In science communication, retire the trope that time will have a final second unless you specify whose time and what mechanism halts it. Ambiguity breeds fake paradox. In personal planning, distinguish between tasks that end with a certificate and tasks that fade, projects. You can close with a last tick versus relationships or skills that dwindle, so you do not punish yourself for not hearing a bell when none can ring. And if you want an honest philosophical takeaway, let it be this. Endings are recognizable when there is a protocol that marks them. Absent such a protocol, lastness is an external description, not an internal experience. The paradox does not tell you that time is illusory or that clocks lie. It tells you that finitude and continuity, locality and record keeping draw the boundary of what last can mean. So if the universe does end, somewhere some clocks will simply fail mid-beat, and everywhere else no tick will be last because none will be next. If it does not, clocks will slow as resources thin, and no tick will deserve the title because the procession will blur into silence. Either way, your craving for an audible full stop is a human hunger for closure, not a demand the world must answer. The gentle wisdom is to build closures where they matter, certificates, rituals, cut-offs, while letting the cosmos keep its open intervals. Why simultaneous is local only. Stand 2 alarms on a long table and try to make them ring at the same time, and you'll discover the quiet rule that runs the modern world. Simultaneous is something you can secure here, between devices that can exchange signals and agree on a convention, but it is not a fact that stretches unbroken across distance. The farther you reach, the more now phrase into a family of choices tied to motion, gravity, and the ways we synchronize. The operational heart is simple enough to carry without equations. To call 2 distant events simultaneous, you must define how to set their clocks. And the most natural recipe, Einstein's, says, send light from A to B, reflect it, and split the round-trip time in half to mark the at the same time on A. Adopt that, and you've fixed a local convention that works beautifully so long as everyone shares a state of rest and space is flat. Start moving though, and the convention slices through space-time tilt. An observer cruising past you who uses the same light exchange rule draws a different now across the map. Events that you pair as co-present, she pairs as before-after, and vice versa. This is not about optical illusions or human delay. It is the geometry of a world in which influences can't outrun light. Because no signal can bridge far points instantaneously, nothing enforces a single global page on which all distant happenings can be printed side by side. What you can enforce are local pages that join smoothly where those signal exchanges actually reach. That's why the safest statements we make about separated events are causal ones. This could have affected that, or could not have, rather than simultaneous ones. The picture tightens when you leave idealized emptiness. In curved space-time, there is no global inertial frame at all. Gravity makes straight world lines bend and prevents a single slicing from staying non-contradictory everywhere. You can define a respectable now along a world line, your own path through space-time, and extend it a little way out, using local inertial coordinates or Fermi slices that are orthogonal to your motion. But as you extend farther, curvature and acceleration shear your slices, and 2 different observers who start nearby will disagree on which distant events they pick up into their present. Even rotation in flat space exposes the limit. Ride around a ring and try to synchronize clocks by Einstein's rule. By the time you complete the lap, you face a mismatch called the Sagnac effect. The loop refuses a single consistent now because the motion itself breaks the symmetry needed for a global agreement. Engineers live with this every day. The navigation in your phone depends on satellites whose onboard clocks are disciplined not to some platonic universal time, but to a coordinate time defined for an Earth-centered reference frame. Ground stations, satellites, and receivers trade signals and corrections, so that when we say two measurements were simultaneous, we mean simultaneous in this chosen frame, after applying motion and gravity adjustments. Financial exchanges, radio telescopes, and power grids adopt similar practices. They publish a timescale, spell out which frame it tracks, and use two-way time transfer to keep devices within microseconds or nanoseconds of that convention. This is how civilization finesses the fact that true simultaneity is local. We build networks whose edges negotiate a shared now by constant conversation, knowing that without that conversation, the phrase, "at the same time," loses sharpness once you separate clocks by any meaningful distance. The payoff for accepting this is clarity about familiar confusions. When a fast train and a platform disagree about whether two lightning strikes hit the ends of the train together, no one is mistaken. Each use the same light-based rule in their own rest frame, and the world offers no absolute referee because signal cones, not nows, are the invariant structure. When people say relativity makes time subjective, it's more honest to answer. It makes simultaneity frame-dependent while leaving cause and effect intact. Your heart still beats in order, your memories remain ordered along your path, and whether A can influence B is a frame-free fact. Even cosmology's reassuring cosmic time, the clock that ticks with the average expansion of the universe, is a special-purpose agreement. It works for observers who drift with the large-scale flow of galaxies, but if you cruise fast relative to that flow, your own slice of now through the cosmos tilts, and the sense that there is one master present dissolves again. This does not trap us in philosophical fog. It gives us design rules. If you build a distributed system, never require nodes to act based on an undefined global instant. Instead, base decisions on messages received and acknowledged, or on timestamps tied to an explicit time service with known uncertainties. If you compare measurements from accelerating platforms, define the frame in which together is to be judged and propagate uncertainties that include the synchronization bias. Do not assume that the word now carries over when hardware changes state of motion. If you plan an experiment that spans kilometers or satellites, ensure your simultaneous triggers are either derived from a common signal distributed to all parties, or are reconstructed afterward by exchanging logs and applying the declared frame's corrections. Otherwise, apparent paradoxes are just unsynchronized notebooks. And when you meet claims that some exotic protocol overturns the rule, instantaneous coordination, action at a distance that can be used to signal, ask which frame's simultaneity they smuggled in. If you remove that crutch and require only local operations and classical communication, the contradictions evaporate, because nature never lets a usable message outrun its light cones. The soft human lesson tucked in here is kind. We crave a single shared present because it makes stories tidy, but the universe gives us something more modest and more workable. Local presence that can be braided by communication and convention into a usable fabric. Once you accept that, you stop arguing over impossible absolutes and start tending the threads, signals, corrections, declared frames that keep the fabric from tearing. You also gain a gentler intuition for experience itself. There is the time inside your reach where you can shake hands with another clock and agree on a moment. There is the time just beyond where agreement costs a little coordination. And there is the time far away where at the same time is not false so much as undefined until you do the work. And with that thought, simultaneity is not a law to discover. It is a relationship to establish. Locally, you can make it crisp. Globally, you can only make it by building it. And that is not a loss. It is a design freedom that, once understood, lets you steer satellites, stitch telescopes across continents into a single eye, and keep the electric beat of cities in phase, all by treating now not as a universal drum, but as a chorus that stays together because each voice listens, answers, and agrees. Is time fundamental or emergent? Start with an unsettling but fruitful question. If you peeled the world down to its deepest rules, would you still find a flowing before, after, or would you meet something static from which our sense of flow is woven the way temperature is woven from molecules? Because deciding whether time is fundamental or emergent changes what we count as an explanation, what experiments we bother to build, and how we make peace with beginnings and ends. On the fundamental side, the case is straightforward to love. Our best dynamical laws are written as evolution rules, and those rules only make sense if there is a parameter that orders change. The geometry of space-time in relativity, even, is a book of causal orderings, with light cones laying down who can influence whom, and precise clocks, atomic, optical, agree so well with that geometry that you can move one a few centimeters and watch its rate shift, as if time were an objective field that responds to place and motion. On the emergent side, the case is sharper than a slogan. Several deep formalisms stop talking like storytellers and start talking like accountants, replacing evolving in time with satisfying a constraint, so that the total description looks timeless until you choose a subsystem to act as a clock. Statistical mechanics shows how an arrow of time arises not from any microscopic bias, but from special initial conditions and the fact that we coarse-grain, letting the number of compatible micro-histories swell until later almost surely contains more ignorance than earlier. Modern quantum field theory often explains behavior by scales rather than moments. Renormalization is a flow in resolution, not in seconds, and in some quantum gravity toy worlds, the very space that hosts time seems to appear as an effective description of more abstract relations, suggesting that what we call when might be just as relational as what we call where. The strongest insight isn't in taking sides, but in noticing that time is a bundle of roles we can test separately. There is ordering, the partial sequence that says which events can influence which. There is duration, the metric that lets clocks agree on how much change happened between marks. There is arrow, the direction we use to organize records, causes, and predictions. And there is experience, the felt flow that stitches moments into a life. Relativity shows that ordering is robustly physical, even if different observers slice now differently. Precision metrology shows that duration behaves like a field's response to gravity and motion. The arrow is mostly a thermodynamic story that depends on low-entropy beginnings and on what information we ignore. Experience rides on predictive brain machinery that anticipates arrivals and writes memories asymmetrically. Once you split the bundle, the alleged contradiction softens. The ordering and metric might be fundamental, or at least part of whatever replaces space-time in a deeper theory, while the arrow and the flow feeling are emergent properties of states like ours. The next move is experimental, not mystical. If time is truly granular at a tiny scale, many independent clocks flown along different paths should betray the same subtle frequency pixelation or the same universal jitter. We do not see that yet, which corrals discrete time fantasies into models that preserve the observed smoothness at accessible energies. If time's arrow is purely statistical, then by engineering small, isolated systems with tailored initial conditions, we should be able to reverse local arrows without breaking causality. In nanophysics and cold atom labs, we do this already, watching tiny engines run backward for a few cycles, and confirming that the second law is a law of overwhelming odds, not a metaphysical ban. If time's metric emerges from correlations, then different choices of internal clocks in a composite quantum system should give consistent but relational descriptions of the same evolution. Quantum control experiments now stitch such cross-views together, showing that when you pick one part as a clock, the rest does look like it evolves, and that different clock choices agree when you translate between them carefully. If space-time itself is emergent, then high-energy collisions, black hole echoes, or precise patterns in gravitational wave ringdowns might carry signatures of the microscopic scaffolding. We haven't caught any such fingerprint yet, but the search has matured to the point where concrete anomalies, tiny symmetry violations, unexpected dispersion, horizon-scale interference would count. Amid these tests, a sober lesson keeps returning. Our operational access to time always runs through physical clocks and records, not through metaphysical hands. A clock is a system with stable cycles and readout. A record is a physical mark that can be compared. and any claim about time that cannot, even in principle, be cashed out in terms of such devices slides toward poetry. But poetry has its place, and the gentle human question, what should I believe about time, deserves a calm answer. Believe what helps you predict and coordinate. Treat ordering and duration as real enough to steer probes past planets and coordinate continents. Treat the arrow as a contingent feature born from low entropy beginnings and your limited vantage, which is why refrigerators need outlets and stories run left to right. Treat the feeling of flow as your brain's predictive bookkeeping, useful for living, but not a proof of cosmic rivers. Then, keep an open hand for the next rung of theory, because neither camp has closed the case. If a deeper framework one day writes the world as relations and constraints from which ordinary spacetime and its ticking emerge cleanly, we will gain understanding without losing clocks. If, instead, geometry and its light cones survive to the bottom, we'll have learned that some appearances really are fundamentals in disguise. The soft closing is practical as well as reflective. Whether time is fundamental or emergent, the craft of making good seconds remains the same. Build better clocks, compare them honestly, record outcomes you can audit, and remember that much of what you call later is a story you and the universe co-author by choosing what to keep and what to ignore. The deeper truth you seek will not cancel that craft. It will explain why it works so beautifully here, in the moving present, where you live.